Hello and welcome. I'm so glad you're here with me tonight. Find a comfortable position wherever you are. Let your shoulders drop, release any tension you might be holding in your jaw, and take a slow, deep breath. Hold it for just a moment, then now let it go. Tonight we're going on a journey together, a peaceful exploration into one of the most beautiful and fundamental concepts in all of mathematics. We're going to discover how polynomials, these elegant mathematical expressions, are woven into the very fabric of our universe. But don't worry if mathematics hasn't always been your favorite subject. Tonight there are no tests, no pressure, no rushing. We're simply going to wander through ideas together, at a pace that feels calm and natural. Think of this time as a gift you're giving yourself, a chance to let your mind drift through the cosmos of mathematical thought, to see patterns and connections that have been hiding in plain sight all along. The fundamental principle that governs exponential behavior is deceptively simple. Something grows by multiplying itself by a constant factor over and over again. This multiplication, this recursive doubling back upon itself, creates patterns that seem almost alive in their relentless expansion. When we talk about exponential growth, we're speaking of a process where the rate of change is proportional to the current amount. The bigger it gets, the faster it grows. It feeds itself. Consider the humble bacteria in a petri dish. Each microorganism splits into two, not in some linear fashion where we get 2, then 3, then 4. Rather, we get doubling upon doubling. Start with 1. After a certain interval, you have 2. In the next interval, each of those 2 becomes 2, giving you 4, then 8, then 16. The sequence unfolds like a cascade, each step multiplying the previous by a fixed ratio. This ratio, this constant multiplier, is the heartbeat of exponential phenomena. The mathematical underpinning involves a base, which is the number doing the multiplying, and an exponent, which tells us how many times to perform that multiplication. If we use a base of 2 and an exponent of 5, we're saying, take 2 and multiply it by itself 5 times. 2 times 2 equals 4. 4 times 2 equals 8. 8 times 2 equals 16. 16 times 2 equals 32. The answer is 32. But we can think of this more fluidly. The base represents what factor we're repeatedly applying, and the exponent represents the number of applications. There exists a remarkable number in mathematics, an irrational constant that appears everywhere in nature and growth phenomena. It's approximately 2.7182,81828, continuing infinitely without repeating. This number is called E. It emerges naturally from compound growth, from continuous multiplication, from the way populations proliferate and radioactive elements decay, and money accumulates with interest. Euler discovered its deep significance, and it became the foundation for the most elegant of all exponential expressions, e raised to the power of x. When we use e as our base, something peculiar and beautiful happens. The rate of growth at any point equals the total amount present at that point. This self-referential quality, this feedback loop between a function and its rate of change, makes e fundamentally important. It's not arbitrary that e keeps appearing. It's the only base where the derivative of the exponential function equals the function itself. For linear growth, the rate of change is constant. For exponential growth using base e, the rate of change is always proportional to what you have, which is the most natural way for growth to occur in the real world. The contrast between exponential and polynomial growth illuminates why exponentials are so powerful, and in many cases so frightening. Suppose we have a polynomial function that grows as x to the third power. For small values, this polynomial is substantial. When x equals 2, we get 8. When x equals 3, we get 27. When x equals 4, we get 64. Then now compare this to 2 raised to the power of x. When x equals 2, we get 4. When x equals 3, we get 8. When x equals 4, we get 16. Initially, the polynomial seems larger. But continue forward. At x equals 10, the polynomial gives us 1000. The exponential gives us over 1000. At x equals 20, the polynomial gives us 8000. The exponential gives us over 1 million. The gap widens with each step, and eventually the exponential function utterly dominates, leaving the polynomial function in the dust, no matter how high the degree of that polynomial. This property, that exponential functions eventually outpace any polynomial function, has profound implications. It means that exponential processes, whether they're spreading viruses, accumulating wealth, or consuming resources, will eventually become all-consuming if left uninterrupted. This is why exponential growth is simultaneously fascinating and alarming. In favorable circumstances, it's the engine of wealth creation and technological progress. Under unfavorable circumstances, it's the mechanism of collapse and catastrophe. The inverse of exponential growth is exponential decay. If growth means repeatedly multiplying by something larger than 1, decay means repeatedly multiplying by something between 0 and 1. Imagine a substance that loses half its mass every hour. Start with 100 units. After 1 hour you have 50. After 2 hours you have 25. After 3 hours you have 12.5. The pattern is familiar but moving in the opposite direction. The amount shrinks, but it never quite reaches 0. It approaches 0 asymptotically, getting closer and closer but remaining positive forever. This is the nature of decay. It's infinite in its patience, asymptotic in its approach to nothing. Radioactive decay follows exactly this pattern. Every isotope has a half-life, the time it takes for half of any given sample to decay into a different element. Carbon-14 has a half-life of about 5,700 years. This means if you have a piece of wood with a certain amount of carbon-14 today, in 5,700 years, half that carbon-14 will have transformed into nitrogen-14. This fact becomes the basis for radiocarbon dating. By measuring how much carbon-14 remains in an ancient artifact, scientists can determine how many half-lives have passed, and therefore how old the artifact is. The formula for decay uses e raised to the power of a negative value. This negative exponent is what causes the decline. When the exponent is negative, raising e to that power gives you a fraction, a number between 0 and 1. Multiplying by a number less than 1 makes quantities shrink. The initial amount multiplied by e raised to 1, negative k times t, where k determines the rate of decay and t represents time, gives you the remaining amount. The larger k is, the faster the decay. The longer t is, the more decay has occurred. The logarithm is the inverse operation of exponentiation. If exponentiation asks the question, what do you get when you raise this base to this power? Logarithm asks, to what power must I raise this base to get this result? If 2 raised to the power of 3 equals 8, then the logarithm base 2 of 8 equals 3. Logarithms turn multiplication into addition, which is why they were so valuable before computers existed. The table of logarithms allowed people to convert complex multiplication problems into simple addition problems. Perform the addition, then convert back. The common logarithm uses base 10. The natural logarithm uses base e. The natural logarithm is written as len, and it's the inverse of the exponential function with base e. If you have e raised to x, the natural logarithm of that result is x. This inverse relationship is crucial for solving exponential equations. When you need to find the exponent, when you need to work backwards from a result to determine how many steps it took to get there, logarithms are your tool. Exponential equations appear throughout science and engineering. The charging of a capacitor follows an exponential curve. It doesn't charge at a steady rate. Instead, it charges quickly at first, when the voltage difference is greatest, then more slowly, as it approaches full charge. The charging curve is 1 minus e raised to negative t divided by RC, where R and C are properties of the circuit. Similarly, the discharge of a capacitor, when it's connected to a resistor, with no external power source, follows e raised to negative t divided by RC. The capacitor empties itself in an exponential manner. Newton's law of cooling describes how hot objects lose heat to their environment. A cup of tea starts hot. It cools down quickly, initially when the temperature difference between the tea and the room is greatest. As it approaches room temperature, it cools more slowly. The temperature at any time is the room temperature plus the initial temperature difference, multiplied by e raised to negative k times t. The constant k depends on properties like insulation and the nature of the surroundings. This is why cooling curves are convex initially, then flatten out asymptotically. In finance, compound interest demonstrates exponential growth with particular clarity. If you invest a sum of money at a given interest rate, the amount grows exponentially. The more frequently interest compounds, whether annually, quarterly, monthly, daily, or continuously, the more total growth you achieve. Continuous compounding, calculated using e raised to the power of rate times time, provides the theoretical maximum return. This is why banks advertising compound interest are exploiting exponential behavior. Your money doesn't just grow. It grows faster the more it grows. The interest earns interest, which earns interest, creating a cascade of multiplication. Population dynamics and ecology frequently follow exponential models, at least initially. When a species is introduced into a new environment with abundant resources and few predators, it reproduces exponentially. The population might double every generation, but this can't continue forever. Eventually, resources become limited, waste accumulates, disease spreads more easily in dense populations, and predators discover the resource. The population transitions from exponential growth to logistic growth, where it levels off at some carrying capacity. The logistic function looks like an elongated S shape, starting nearly exponential, then bending to approach a maximum value asymptotically. The concept of doubling time captures the essence of exponential growth intuitively. For any exponential process, there's a specific duration required for the quantity to double. For a bank account earning compound interest, this might be 7 years. For a rapidly growing bacterial colony, this might be 20 minutes. The doubling time depends on the growth rate. Faster growth means shorter doubling times. Using the natural logarithm of 2 divided by the growth rate gives you the doubling time. This simple calculation reveals a profound truth. Exponential processes are deceptive. They seem manageable for a long time, then suddenly become overwhelming. If something doubles every doubling time, then in 10 doubling times, you get a 1,000-fold increase. In 20 doubling times, you get a 1,000,000-fold increase. This hidden acceleration is why epidemiologists worry about exponential disease spread. Early in an outbreak, when cases are doubling every few days, the situation might seem manageable. 20 cases, 40 cases, 80 cases. The public might not be alarmed, but if doubling continues unchecked, that exponential progression leads inexorably to overwhelming healthcare systems, exhausted resources, and cascade failures throughout society. Similarly, in environmental science, the exponential growth of resource consumption and waste production has brought humanity to the edge of planetary boundaries. The trajectory doesn't show a linear approach to limits. It accelerates. Half-life, the decay side equivalent of doubling time, helps us think about radioactive and other decay processes. Plutonium-239 has a half-life of 24,000 years. This means a sample left undisturbed will still be 50% of its original amount in 24 millennia. This extraordinarily long half-life explains why nuclear waste remains hazardous for spans of time that exceed recorded human history. Conversely, iodine-131, produced in nuclear accidents, has a half-life of only 8 days. It's dangerous acutely, but largely disappears within months. The half-life determines the timescale over which decay is significant. The mathematical limit that defines E involves the concept of continuous compounding taken to its extreme. Imagine compounding interest, not yearly, not daily, but infinitely frequently, with infinitely many compounding periods per year. The calculation of this limit, the limiting value of 1 plus 1 divided by n, raised to the power of n, as n approaches infinity, converges to E. This limit reveals that E emerges not from arbitrary choice, but from the natural structure of continuous growth. It's the answer to the question, what do you get when you compound infinitely frequently at a rate of 100% per unit time? The graph of an exponential function shows distinctive characteristics. If the base is greater than 1, the graph curves upward, showing growth. The curve is convex, meaning it bends upward, increasingly steeply. At the left, where x is negative, the function approaches 0 asymptotically. At the right, where x is positive, the function shoots skyward without limit. The point where x equals 0 is special. Any positive number raised to the power of 0 equals 1. So every exponential function crosses the y-axis at the point 1. This single point of intersection is a signature of exponential functions. For decay, with a base between 0 and 1, the graph is flipped horizontally in character. The function starts high when x is negative, descends as x increases, and approaches 0 asymptotically for large positive x. Again, the function passes through the point 1 when x is 0. The curve is concave, bending downward as it falls toward the horizontal axis. Transformations of exponential functions shift and stretch these characteristic curves. Adding a constant to the exponent shifts the graph horizontally. Multiplying the entire function by a constant stretches it vertically. Adding a constant to the entire function shifts it vertically, which also shifts the horizontal asymptote. These transformations preserve the essential exponential character while altering appearance. The concept of an asymptote is fundamental to understanding exponential behavior. An asymptote is a line that a function approaches arbitrarily closely, but never quite reaches. For exponential decay, the horizontal line at 0 is the asymptote. No matter how much time passes, the remaining amount never becomes exactly 0, though it gets infinitesimally close. For shifted decay functions, the asymptote might be at some value above 0, representing a baseline that the function approaches. The derivative of an exponential function reveals its growth rate at any instant. For a general exponential function with base b, the derivative involves multiplying the original function by the natural logarithm of the base. This means the rate of change is always proportional to the function value itself. For the special case of e raised to x, The derivative is simply e raised to x. The function and its rate of change are identical. This self-referential property makes base e fundamental in calculus, and in modeling real-world continuous phenomena. In systems of differential equations, exponential functions appear as solutions constantly. Any system where the rate of change of a quantity is proportional to the quantity itself generates exponential solutions. This encompasses diverse phenomena: radioactive decay, population growth with unlimited resources, cooling by radiation, certain chemical reactions, and the spread of epidemics before external constraints take effect. The structure of the underlying mathematics guarantees exponential behavior. The integral of an exponential function also involves the same beautiful property. Integrating e raised to x gives you e raised to x again, plus a constant of integration. For other bases, the integral requires dividing by the natural logarithm of the base. This structure reflects the deep connection between exponentiation and integration in calculus. Complex exponentials extend the concept into the realm of complex numbers, where the real and imaginary parts interact in sophisticated ways. Euler's formula relates complex exponentials to trigonometric functions through the identity e raised to I times x equals cosine of x plus I times sine of x. This identity, where I is the imaginary unit, reveals a profound connection between exponential growth and circular motion. Rotating motion can be described as exponential growth in the complex plane, while exponential growth can be understood as rotation combined with scaling in that plane. The power series expansion of exponential functions shows that they're the sum of infinitely many polynomial terms. E raised to x equals the infinite series 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the fourth divided by 4 factorial, and so on. This representation reveals that exponential functions are built from polynomials, yet behave in fundamentally different ways due to the infinite summation structure. In probability and statistics, the exponential distribution models the time between events in a Poisson process, random occurrences that happen at a constant average rate. The probability that the waiting time exceeds t is e raised to negative lambda times t, where lambda is the rate parameter. This means the probability of waiting a long time decreases exponentially. This distribution appears in many contexts: the time until a radioactive atom decays, the time until the next customer arrives at a service counter, the time until a light bulb burns out, and numerous other phenomena governed by memoryless processes. The concept of exponential growth in networks manifests in the propagation of information, influence, and disease through interconnected systems. When each infected individual or converted node in a network connects to multiple others, the cascade of adoption follows exponential patterns initially. This is why social media platforms can seem to explode in user base, why internet memes spread virally, and why pandemics in an unvaccinated population can rapidly overwhelm healthcare capacity. The network structure amplifies the exponential dynamics, creating explosive growth. Saturation effects and resource constraints eventually limit all exponential growth in real systems. The logistic growth model captures this by introducing a carrying capacity, a maximum sustainable population or quantity. The growth rate becomes proportional not just to the current amount, but to the difference between the current amount and the carrying capacity. Near zero, when resources are abundant, growth is nearly exponential. As the amount approaches the carrying capacity, growth slows dramatically. The result is the characteristic S-shaped curve, where initial exponential growth transitions smoothly to saturation. The critical difference between linear and exponential thinking has implications for human intuition and decision-making. Humans evolved to think in linear terms. We expect change to proceed at steady rates. We're biased toward underestimating exponential growth when it's beginning, because the numbers seem small and manageable. Conversely, we're often shocked when exponential processes suddenly accelerate into crises. Climate change, technological disruption, and pandemic spread all reflect exponential dynamics that outpace our intuitive linear expectations. The noise in systems with exponential behavior becomes amplified. Small perturbations or uncertainties in initial conditions can grow exponentially, leading to dramatically different long-term outcomes. This is the essence of chaos theory: sensitive dependence on initial conditions. In weather systems, the famous butterfly effect captures this concept. A butterfly flapping its wings in Brazil sets off a chain of events that, through exponential amplification of tiny perturbations, could theoretically influence the formation of a tornado in Texas. Exact long-term prediction becomes impossible, even though the underlying equations are deterministic. Exponential smoothing techniques and time series analysis use weighted averages where recent observations receive exponentially higher weights than older ones. This approach captures recent trends while being robust to noise. It's used extensively in forecasting, inventory management, and financial analysis. The method gives more credence to recent data, recognizing that in systems that change exponentially, or are influenced by exponential processes, the past may be a poor guide to the immediate future. The concept of exponential backoff appears in computer networking and error handling. When a system fails to complete a task, exponential backoff strategies increase the wait time before retry attempts, typically doubling the wait each time. After failing once, wait a second. After failing twice, wait 2 seconds. Then 4. Then 8. This protects systems from cascading failures where too many simultaneous retries create additional load, making recovery harder. The exponential scaling ensures that the system eventually backs off to a rate where recovery becomes possible. In genomics and molecular biology, the polymerase chain reaction, or PCR, amplifies DNA exponentially. Each cycle of the PCR process doubles the number of DNA copies in the reaction mixture. Starting with perhaps a few hundred target molecules, after 30 cycles of doubling, you have billions of copies. This exponential amplification is what makes PCR so powerful in diagnostics, forensics, and research. The same exponential principle underlies viral replication, where each infected cell produces many copies of a virus, which then infect more cells, leading to exponential spread. The relationship between exponential functions and logarithms extends to data analysis and visualization. When data spans multiple orders of magnitude, meaning the largest values are thousands or millions of times larger than the smallest linear scales become useless. Logarithmic scales compress this range. On a logarithmic scale, each tick represents multiplication by a fixed factor, usually 10. This allows exponential growth to appear as a straight line, making it easier to identify and analyze. Stock market charts, earthquake magnitudes, and sound intensity levels all use logarithmic scales, precisely because the phenomena being measured exhibit exponential, or power law behavior. The rate of exponential growth determines whether a system survives or collapses in the presence of resource constraints. If the population growth rate exceeds the rate at which the environment can replenish resources, collapse is inevitable. Conversely, if resource regeneration outpaces consumption, stability is possible. This dynamic appears in fisheries management, forest harvesting, groundwater extraction, and agricultural practices. The mathematics is inexorable. Exponential growth of consumption, meaning constant or slowly increasing resource availability, creates an intersection point, and beyond that point, only collapse remains. Understanding exponential functions is perhaps one of the most practically important concepts in mathematics. It appears everywhere, in finance planning, public health, environmental science, technology adoption, nuclear engineering, and countless other domains. The gap between intuitive human judgment and exponential reality has become the source of many modern problems, from accumulated debt to climate change to resource depletion. Building accurate intuitions about exponential behavior, recognizing when processes are exponential, understanding doubling times and half-lives, grasping why saturation eventually occurs, is essential for informed decision-making in an increasingly complex world where exponential processes shape our future. The morning light filtered through the library windows like honey through gauze, and somewhere in that golden haze, a student named Maya was about to discover something that would change how she understood growth itself. She'd been studying exponentials for weeks now, moving through the landscape of powers and bases with increasing confidence. But today, her professor handed her a different kind of problem, one that didn't fit neatly into the pattern she had memorized. It was a problem about mixing, about dilution, about how something gradually becomes less of itself over time. The setup was simple enough. The container held 100 units of some substance, let's say it was dye dissolved in water, glowing and vivid. Every minute 1/10 of whatever currently remained would be removed and replaced with pure water. What would happen as time went on? How much dye would remain after many minutes? Maya set up the problem methodically. At the start there were 100 units. After 1 minute of removal and replacement, 9/10 remained, so she had 90 units. After the second minute, she removed 1/10 of 90, which left her with 81 units. Then came 72.9 units, then 65.6, and 1 units, and so on, each time multiplying by 0.9. After minute 1, 100 times 0.9 equals 90. After minute 2, 100 times 0.9 times 0.9 equals 81. After minute 3, 100 times 0.9 to the third power equals 72.9. The pattern crystallized. After n minutes, the amount remaining would be 100 times 0.9 raised to the power n. But here is where something unexpected emerged. As n grew larger and larger, the amount didn't just decrease smoothly towards zero. It approached zero in a way that was mathematically beautiful, like watching a melody gradually fade into silence. After 10 minutes, she calculated, 100 times 0.9 to the 10th power equaled roughly 35.89 units. Half of the original die had already vanished. After 20 minutes, 12.16 units remained. After 50 minutes, the amount was so small it barely registered, 0.57 units. And mathematically, no matter how many minutes passed, it would never quite reach exactly zero. It would approach zero asymptotically, like a bird flying toward the horizon, always closer but never arriving. This was the essence of exponential decay, and it was fundamentally different from the exponential growth she had studied before. Her professor, noticing a shift in Maya's expression, asked her to think about what was happening. She explained that in growth, you multiply by something larger than 1 each step, so the numbers climb higher and higher. In decay, you multiply by something smaller than 1, something between 0 and 1, and the numbers shrink toward nothing without ever quite touching it. The professor nodded and then extended the thought. Imagine, he said, that the base of your exponential wasn't just any number between 0 and 1. Imagine it was specifically 1 divided by e, or e was that famous mathematical constant, approximately equal to 2.71828. 1 divided by e is roughly 0.36788. So if you had a function where the value was the starting amount times 1 divided by e to the power t, what happened? After 1 unit of time, you would have the starting amount multiplied by approximately 0.36788. You would retain roughly 36.788%. After 2 units of time, you would multiply by 0.36788 again, getting roughly 13.533% of the original. After 3 units of time, roughly 4.978% remained. After 5 units of time, roughly 0.673% persisted. The function was falling away rapidly, yet always maintaining that elegant mathematical property. At every instant, the rate at which it was falling was proportional to its current height. Maya felt something click into place. She realized that exponential decay wasn't just about dilutions or disappearances. It was about radioactivity, where atoms broke down at a rate proportional to how many atoms remained. It described the cooling of a hot object in a cold room. It described how medications filtered from your bloodstream. It described how loudness diminished as you moved away from a speaker, how light faded through water, how heat escaped from insulation. But her professor pushed further. He asked her to think about what happened if you combined growth and decay. What if you had a situation where something was increasing exponentially at a certain rate, while simultaneously being removed or lost at another rate? This was trickier, and Maya leaned back in her chair, considering. Her professor gave her an example from biology, bacteria in a petri dish. Suppose the bacteria population doubled every hour if left completely undisturbed. That would be exponential growth with a doubling time of 1 hour. But suppose every hour someone also removed half the dish. That was exponential decay happening at the same time. So the question became, would the population grow, shrink, or stabilize? Maya worked through a concrete example. Start with 100 bacteria. After 1 hour, without removal, there would be 200 bacteria. But with removal of half the dish, the 200 would become 100. After the next hour, the 100 would double to 200, then be reduced to 100 again. The population, Maya realized, would stabilize at 100. Growth and decay would balance perfectly, and the population would hover at that equilibrium point. But what if the removal rate was different? Well, someone removed only 30% of the dish each hour. Then, starting with 100 bacteria, after 1 hour there would be 200, and removing 30% would leave 140. After the next hour, 280, reduced by 30% to 196. The population would climb, though more slowly, approaching some maximum value. That maximum was where the growth exactly balanced the loss. Or what if the removal was 90% each hour? Then starting with 100, doubling to 200, then 90% removed would leave only 20. The next hour, 40, then 4. The population would crash toward zero. It all depended on the relative rates, the speed of growth versus the speed of decay. Maya's professor then introduced her to a more subtle version of this balance. In real applications, he explained, things often didn't happen in discrete steps. Instead, change was continuous. The population might grow every instant, not just every hour. Loss might happen constantly, not just in pulses. This continuous compounding and continuous decay led to differential equations, which were mathematical descriptions of how something changed at every moment based on its current state. For exponential growth, the simplest differential equation was that the rate of change of something was proportional to the thing itself. If p was the population and t was time, then the rate of change of p, written as dp divided by dt, equal the constant k times p. This constant k was the growth rate. If k was positive, the population grew exponentially. If k was negative, it decayed exponentially. If k was 0, nothing changed. The solution to this equation, Maya learned, was that p at time t equaled the starting population times e, raised to the power k times t. There was that constant e again, appearing as naturally as breathing, in the solution to this fundamental differential equation. It wasn't arbitrary or invented for you. Convenience. It emerged because e had this unique property. When you raised e to any power, the rate at which that exponential changed was exactly equal to itself. If you had e to the power x, and you asked how fast it was changing with respect to x, the answer was exactly e to the power x. No constants, no adjustments needed. This self-derivative property made e special, almost inevitable, in describing processes where the rate of change depended on the current value. Maya began to see exponentials as not just mathematical tools, but as expressions of something fundamental about the natural world. When a process was driven entirely by its current state, when growth or decay was intrinsic, rather than imposed externally, exponentials appeared. They were the default pattern when things were left to their own devices, following only the rules of their own nature. Her professor gave her another perspective. He asked her to imagine a substance that was radioactive, with a half-life of 1,000 years. A half-life, he explained, was the time it took for exactly half of a radioactive sample to decay. If you started with 1 million atoms, after 1,000 years, 500,000 would remain. After 2,000 years, 250,000. After 3,000 years, 125,000. But here was the key insight. The same half-life described the entire decay process simultaneously. You didn't need to know anything else about the substance's behavior. The half-life alone was sufficient to predict the amount of any future time. Starting with an amount a, the amount remaining after time, t, would be a times 1/2 raised to the power of t, divided by the half-life. If the half-life was 1,000 years, and you wanted to know how much remained after 3,000 years, you would calculate a times 1/2 to the power of 3, which was 1/8 of the original. If you wanted to know how much remained after just 500 years, you would use 1/2 to the power of 0.5, which was 1 divided by the square root of 2, roughly 0.707, so about 70.7% would remain. The beauty of this formulation was that it worked for any time interval, not just multiples of the half-life. The exponential nature of radioactive decay meant that the decay process was self-similar. It looked the same at any time scale. This self-similarity connected back to that fundamental property of exponentials. The rate at which something decayed was always proportional to how much of it remained. Whether you looked at the decay over a year, the day, an hour, or a second, the pattern held. This proportionality was what gave exponentials their characteristic smoothness and unity. Maya asked her professor about the opposite scenario. What if you started with 0 something, and it was being created at a rate proportional to some maximum value it could never quite reach? He smiled and described a classic scenario. The person receiving treatment for an infection. They were given antibiotics that could eliminate the infection, but they were also receiving new infections from exposure. The rate at which they recovered was proportional to how much infection remained. The rate at which new infection came in was constant. Let's say 1 unit per day, representing continuous exposure. The infection level would climb initially, since exposure was happening at a fixed rate, while the elimination was slow at first. But as the infection level rose, the elimination would speed up. Eventually, the elimination would exactly match the exposure, and the infection level would stabilize at some equilibrium. That equilibrium would be where the exponential growth from exposure exactly balanced the exponential decay from treatment. And the path toward that equilibrium would follow an exponential curve, approaching the equilibrium from below, if starting healthy, or approaching from above the starting with a serious infection. The general solution to this kind of problem, her professor explained, would be an exponential approaching a horizontal line, an asymptote. If the equilibrium was at some value L, and the current value was p, then after time t, the difference between p and L would have decayed exponentially. So p of t would equal L plus the initial difference times e to the power of negative k times t, where k was the rate constant. This described countless phenomena: how a hot cup of coffee cooled to room temperature, how a population approached carrying capacity in an environment, how a chemical reaction approached equilibrium, how pressure in the sealed container equilibrated, how rumors spread through a population then saturated, how the charge on a capacitor built up through a resistor. Maya was beginning to feel that exponentials were woven into the fabric of change itself. Her professor then posed a problem that combined decay with a twist. Suppose you've had a radioactive substance with a half-life of 10 years, and you also kept adding more of the substance at a constant rate. Say you added 1 unit every month. How much substance would accumulate over time? This was neither pure growth nor pure decay. It was a driven system where decay was happening, but being partially offset by continuous addition. The solution would build up toward an equilibrium point. At that equilibrium, the amount being added per month would exactly equal the amount being lost through radioactive decay per month. Before reaching equilibrium, the amount could grow exponentially toward that limit. After reaching equilibrium, it would remain constant. The path toward equilibrium would follow the same exponential curve pattern. The distance from equilibrium would decay exponentially. This was a profound insight. Whether you were approaching an equilibrium from above or below, whether the equilibrium was 0 or some large number, the pattern of approach was always exponential. The form of the solution didn't change. Only the parameters changed. Maya's professor then asked her to think about a situation with 2 competing populations, predators and prey, or 2 competing species, or even 2 computer processes competing for resources. Let's say you had rabbits and foxes. The rabbit population grew exponentially without predation, say with a growth rate such that it doubled every 2 years. The fox population ate rabbits and grew at a rate proportional to how many rabbits were available. But foxes also died when rabbits were scarce, so their population declined exponentially in the absence of food. This was the famous Lotka-Volterra model, and it produced oscillating cycles rather than exponential curves. But the exponentials were still underlying it. The growth of rabbits in a fox-free environment was exponential. The decline of foxes without enough food was exponential. It was only when you combine these 2 exponential processes together with coupling between them that he got the complex oscillations. These oscillations, Maya realized, were still fundamentally driven by exponential processes, just layered on top of each other and coupled in intricate ways. She began to understand that exponentials weren't just simple curves for simple scenarios. They were building blocks. You could compose them, modify them, couple them together to create almost any kind of behavior. A sum of exponentials with different rates could approximate any smooth curve you wanted. This was the foundation of Fourier analysis and signal processing, though her professor didn't push her that far yet. Instead, he gave her a more practical observation. Many complex systems, when analyzed near their equilibrium points, could be approximated as exponential processes. This linearization, as it was called, meant that understanding exponentials was key to understanding how systems recovered from disturbances, how they oscillated, how fast they stabilized. A stable system was one where perturbations decayed exponentially. An unstable system was one where they grew exponentially. A marginally stable system had neither growth nor decay, hovering at a critical point. This classification applied everywhere: in economics, ecology, engineering, psychology, sociology. The exponential, in its various forms, was the fundamental pattern of response. Maya then asked about something that had been bothering her. In all the examples so far, either growth or decay. But what if the rate of change wasn't constant? What if a population's growth rate decreased as the population grew larger, due to competition or resource limitation? Her professor introduced her to the logistic equation. Instead of the rate of change being simply proportional to the current population, it was proportional to the population, multiplied by the difference between the maximum capacity and the current population. This created a self-regulating system. The logistic equation, when solved, gave a curve that looked like an S shape. It started out growing exponentially when the population was small, then slowed down as it approached the carrying capacity, ultimately leveling off asymptotically. But here was the key. The initial exponential growth phase was the same as you would get from simple exponential growth. It was only later, as the population got significant relative to the carrying capacity, that the limiting factor kicked in. This was why exponentials were so important in practice. Many real-world systems grew exponentially initially, then saturated or leveled off. The exponential phase was usually the dramatic and important part, the part that caught your attention. The logistic curve just added a boundary on top of that exponential foundation. Maya worked through some numerical examples. With a carrying capacity of 1,000, and starting with one individual and a specific growth rate, she calculated how the population would evolve over time. In the early generations, it looked identical to pure exponential growth. But as it approached 500, the growth started to slow noticeably. As it climbed toward 900, the growth slowed even more. It asymptotically approached 1,000, never quite reaching it, but getting arbitrarily close given enough time. This made sense. When the population was 1, the carrying capacity limit barely mattered. The population was free to grow almost purely exponentially. But when the population was 900, in a capacity of 1,000, the limiting factor strongly suppressed further growth. The available resources per individual had shrunk from 1,000 resources per individual. Her professor then raised an even more interesting scenario. What if the carrying capacity itself wasn't fixed? What if it changed over time due to environmental factors, climate cycles, or external inputs? Then the population curve would become much more complex. It might grow when the carrying capacity was high, shrink when it was low, oscillate if the carrying capacity itself oscillated. The exponential would still be there underneath, but modulated by these changes. This was the beginning of understanding nonlinear dynamics and chaos, her professor suggested. Even with relatively simple rules, systems could produce tremendously complex behavior, but exponentials were still fundamental. They were the local behavior, the response to small perturbations, the generator of bifurcations and transitions. Maya realized that to truly understand complex systems, you had to first understand exponentials deeply. Her professor gave her a final example before they wrapped up the day's discussion. In finance and economics, many processes appeared exponential. Money compounded if interest grew exponentially if left alone. Inflation eroded purchasing power exponentially. Epidemic diseases spread exponentially in their early phases. Technological adoption followed an S-curve, which was again an exponential in the fast growth phase with saturation limits. The mathematics was the same. A fixed fractional return per time period led to exponential growth. A fixed fractional loss per time period led to exponential decay. The base of the exponential was 1 plus the fractional change per period. The time scale was measured in how many periods had elapsed. But here was a subtle point. If the compound period became more and more frequent, what happened? If you compounded interest not annually but monthly, weekly, daily, or continuously, did the growth rate increase? No. In the limit of continuous compounding, the growth rate didn't depend on how frequently you compounded. Instead, it depended on the continuous rate r. Starting with principal p, after time t, at a continuous rate r, you would have p times e to the power of r times t. This is why e appeared everywhere in calculus and continuous systems. It was the base that made continuous compounding work out perfectly. If you used any other base, like 2 or 10, the formula would have an extra correction factor. But with e, everything cancelled out to give the pure exponential. Mathematicians and nature itself have landed on e as the ideal base for exponential growth, and decay precisely because of this property. As Maya left the library that afternoon, the light was changing, turning golden, then amber, creating long shadows across the stone courtyard. She thought about how the light itself was exponentially dimmer further from the sun, how the intensity followed an inverse square law that could be related back to exponentials through calculus. Exponentials weren't just in equations. They were in the texture of the world itself. She realized that what had seemed like disconnected concepts, weeks ago now, formed a unified picture. Growth and decay, compounding and dilution, equilibrium and approach, oscillation and resonance, linearization and stability. All of these were built on the foundation of exponentials. And underlying all of that was a simple, beautiful idea. When the rate of change of something depended only on how much of that something currently existed, then exponential functions described the behavior. This was nature's default pattern for any self-modulating system, any system that regulated itself through feedback between its state and its rate of change. The beauty of exponentials, she thought, was that they were both simple and complex. The formula was simple: a starting amount times a base raised to a power that usually involved time. But what emerged from this simplicity was infinite variety. Explosive growth that could double in a heartbeat, invisible decay that could seem permanent, gentle approaches to equilibrium, self-similar structures that looked the same at different scales. Once you saw exponentials everywhere, once you understood how they behaved, how they approached limits, how they could be composed and modified, you saw the fundamental patterns that shaped change itself. As she walked, Maya realized she couldn't unknow this. Every phenomenon that involved growth or decline, every natural system that regulated itself, now showed her its exponential skeleton underneath. It was like learning to see the structure of a building beneath its facade. And yet, having understood this, she was ready for the next layer. She knew that most real systems weren't purely exponential. They were governed by exponentials in combination, exponentials with varying rates, exponentials modulated by external forces, exponentials approaching boundaries. The exponentials were the foundation, but the symphony was built from many foundations playing together. This was where her journey with exponentials was heading, not toward mastery of a simple formula, but toward appreciation of how that simple formula generated the almost bewildering complexity of the natural world, allowed to express itself in different ways, at different scales, in different combinations. The evening had fully arrived by the time she reached her room. Through the window, stars were becoming visible in the darkening sky, each one a distant sun, perhaps with planets circling it, perhaps with phenomena unfolding according to the same mathematical laws she had spent the day studying. Exponential growth in some nebulae, birthing new stars, exponential decay in the dying radiation of old ones. The universe itself an expression of these fundamental patterns playing out across incomprehensible distances and timeframes. She opened her notebook and began working through the problems her professor had assigned. The calculations flowed more smoothly now, not because they had become easy, but because she understood what she was calculating. She wasn't manipulating symbols in a vacuum. She was translating the language of change itself. In the quiet of the night, with her equations before her and her understanding deepening, Maya felt the satisfaction that came from seeing how the world actually worked. Exponentials were more than a chapter in a math book. They were one of the fundamental sentences in the alphabet that nature used to describe itself. The journey through exponentials begins not with formulas, but with understanding a simple human truth. Some things grow in ways that feel almost impossible to track. A single cell divides into 2, then 4, then 8. A whisper carries through a crowd, touching one person who tells another who tells another. These are the stories exponentials tell, and they're everywhere in the fabric of how the world actually works. Imagine you're standing in a garden at dawn. The light is soft and diffused, barely touching the leaves. The growth you see around you doesn't announce itself with sharp edges or obvious changes. A plant grows taller by a small amount each day, so small you might not notice if you weren't paying attention. But exponential growth operates on a different principle entirely. It's growth that feeds itself, that becomes more forceful the further it travels. Think of a bank account earning interest. You deposit money, and the bank pays you a small percentage each year. This percentage is calculated on what you have, not on what you started with. Next year, the bank calculates interest on that larger amount. The year after, on an even larger amount. The growth doesn't stay steady, it accelerates. This acceleration is the heartbeat of exponential behavior. The mathematical heart of this concept rests on a base number and a power. When you raise a number to successive powers, you're essentially multiplying it by itself again and again. Start with 2, and raise it to the first power, you get 2. Raise it to the second power, you get 4. To the third power, 8. To the fourth, 16. To the fifth, 32. Notice how quickly the numbers swell. By the time you reach the 10th power you have over 1,000. By the 20th power, over 1,000,000. The base number matters tremendously. If your base is larger than 1, the numbers climb ever faster. If your base is between 0 and 1, the opposite happens. The numbers shrink, approaching 0 from above, getting smaller and smaller but never quite reaching nothing. This distinction separates worlds of different behavior, different futures. There's a special base that appears again and again in nature, in growth patterns, in the mathematics of change itself. This base is approximately 2.718, though the digits continue infinitely without repeating in any pattern. Mathematicians call it E, named after the mathematician Leonhard Euler, who explored its properties so thoroughly. This number emerges when you consider continuous growth, the kind that happens smoothly without pause. Imagine taking that interest calculation we discussed earlier, and making it happen not yearly, but monthly, then daily, then every hour, then every minute, approaching the limit where it happens constantly, without interruption. The magic of E is that it describes exactly this scenario. The growth rate when compounding happens without bound, continuously, and smoothly. Let's think about how exponential equations actually work in the language of everyday thinking. When something follows exponential growth with a particular base and particular exponent, you're describing a situation where the amount at any moment depends on when you measure and what rate governs the change. The equation that captures this involves multiplying an initial amount by the base raised to a power that increases with time. Picture bacteria in a petri dish. You start with a single bacterium. Every 20 minutes, it divides into 2. After 20 minutes, you have 2 bacteria. After 40 minutes, 4. After an hour, 8. After 2 hours, 64. After 4 hours, 4096. The growth seems gentle at first, then suddenly explodes. This is the deceptive nature of exponential behavior. Early on it seems manageable, almost unremarkable, but given time it becomes unstoppable. The rate at which something grows exponentially connects intimately to the base you're at. Using a base of 1.5 means each time period multiplies the quantity by 1.5. The base of 3 multiplies it by 3. The base of 1.01 means growth. So slow it might barely be noticeable over days or weeks, but over years it compounds into something significant. A base of 0.5 means having each time period, as with radioactive decay or medicine, leading your bloodstream. Understanding the inverse relationship is equally important. If exponential growth describes multiplication, then the opposite process describes division repeatedly. If exponential growth with a base greater than 1 climbs towards infinity, then exponential decay with a base between 0 and 1 descends towards 0. These aren't separate phenomena, they're two faces of the same underlying principle. The language mathematicians use to describe exponential behavior includes the concept of a growth rate or decay rate, and this rate tells you how quickly things change from one moment to the next. A growth rate of 10% per year means the quantity becomes 1.1 times what it was. A growth rate of 50% means it becomes 1.5 times what it was. These rates determine the base of your exponential function. You can convert between thinking in terms of rates and thinking in terms of bases. They're two ways of describing the same underlying dynamic. There's a peculiar and beautiful property of exponential functions with base e. When you take the derivative, which measures how quickly something changes at any instant, you get the original function back, multiplied by the rate. This means the rate of change is proportional to the current amount, which is exactly what defines exponential growth in the first place. Money earning interest grows by an amount proportional to how much money you have. Populations reproduce in numbers proportional to their current size. Disease spreads through numbers proportional to how many people are infected. This self-similarity, where the rate of change depends on the current state, is what makes the function exponential. Connecting exponential growth to real-world timelines helps anchor these abstract ideas. Suppose you're tracking a viral video gaining views. It starts with one person watching. That person shares it with 3 others. Each of those shares it with 3 more. At first, the numbers are tiny. 1 person, then 4, then 13, then 40. But continue this pattern, and by the time the video has been shared, 10 layers deep, you're looking at nearly 60,000 viewers. After just 20 layers of sharing, assuming each person reaches 3 new viewers, they're discussing over 3 billion people, which exceeds the current world population. This impossibility is precisely why exponential growth hits a wall in reality. Resources run out, markets saturate, or the conditions that enable the exponential pattern change. The logarithm exists as the inverse of exponential function, a way to undo the exponentiation. If raising a base to a power gives you a result, taking the logarithm of that result with the same base gives you back the power. This becomes incredibly useful when you're trying to solve problems where exponentials are involved. If you know a population doubles every 10 years, and you want to find when it will reach a certain size, you use logarithms to extract the answer from the exponential relationship. The mathematics of comparing exponential growth to linear growth illustrates why exponentials seem to violate intuition. Linear growth adds the same amount each time period. Exponential growth multiplies by the same factor. Initially, linear growth might actually be ahead, but as time extends, exponential growth always eventually overtakes linear growth and leaves it behind by an ever-widening margin. A line extends forever at a steady slope, but an exponential curve bends upward with increasing steepness, becoming nearly vertical at its edges. Consider the chessboard legend, where a king promises reward to a wise person by placing 1 grain of rice on the first square of a chessboard, then doubling the amount on each successive square. The first square holds 1 grain, the second square holds 2, the third holds 4. By the 8th square, you have 256 grains. But by the 32nd square, you're discussing over 4 billion grains. And by the final square, the 64th, you need more rice than exists in the world. The king's treasury empties before the board is half full, because exponential growth with a base of 2 is relentless. The number here appears not just in abstract mathematics, but in phenomena observed in nature. It emerges in the physics of cooling objects, where hot things lose heat at a rate proportional to how much hotter they are than their surroundings. It describes radioactive decay, where unstable atoms transform into stable ones at a constant fractional rate. It captures the growth of populations under ideal conditions. It even appears in the mathematics of probability and statistics, underlying distributions that describe everything from the heights of people to the lifespans of light bulbs. When you study exponential equations more carefully, you realize they come in various forms, each revealing different aspects of the underlying behavior. The simplest form multiplies an initial amount by a base raised to a time variable. A slightly more complex form includes a rate constant that catches how fast the exponential process is happening. An even richer form might include multiple exponential processes competing or interacting, as happens when predator and prey populations affect each other, or when a disease spreads while simultaneously burning through available hosts. The concept of half-life exemplifies exponential decay in a way that's easy to grasp. Carbon-14, a radioactive isotope used in dating archaeological discoveries, has a half-life of about 5,700 years. This means if you start with 100 atoms of carbon-14, after 5,700 years, you'll have 50 atoms remaining. After another 5,700 years, 25 atoms. The atoms don't disappear all at once. They transform at a rate proportional to how many are present. This is exponential decay, with a base of 1/2 per half-life period. Thinking about doubling time versus half-life provides intuition for how exponential processes feel to humans. If something doubles every 10 years, people barely notice the first doubling. By the second doubling, the change becomes visible. By the third or fourth, observers become shocked at how much has changed. By the 10th doubling, something that started at 1 unit is now at over 1,000 units. Conversely, if something halves every 10 years, it seems to linger almost forever, before finally becoming negligible. A radioactive substance still contains 90% of its atoms after one half-life if you count differently. It's only lost half, but after 10 half-lives, it's less than 1,000th of the original amount. The practical application of understanding exponentials extends into epidemiology, where the exponential model describes how infections spread early in an outbreak. Each infected person infects a certain average number of others, and those infected people each infect more, creating a branching pattern. If each person infects fewer than one person on average, the disease dies out. If each infects exactly one person on average, the disease maintains a steady prevalence. If each infects more than one person, the disease grows exponentially. This basic framework has guided public health responses to pandemics, with quarantines and vaccinations designed to lower the transmission rate below the critical threshold. Computing with exponentials reveals practical challenges. Very large exponentials become difficult to work with directly. Because computers have limits on the size of numbers they can represent, very small exponentials approach zero, so gradually that detecting them requires extreme precision. This is where logarithms become essential tools. Instead of working with the exponential numbers directly, you work with their logarithms, perform calculations in that transformed space, then convert back to exponential numbers when needed. The logarithm of a product equals the sum of the logarithms of its factors. The logarithm of a quotient equals the logarithm of the numerator minus the logarithm of the denominator. The logarithm of something raised to a power equals that power multiplied by the logarithm of the base. These properties transform multiplication and exponentiation into addition and multiplication, which are far simpler to handle. For centuries, before calculators existed, logarithm tables allowed people to perform complex calculations by converting multiplication to addition, working through the problem, then converting back. When you graph an exponential function with a linear scale on both axes, you see a curve that starts nearly flat near the horizontal axis, then bends upward with increasing steepness. But if you graph the same exponential function on a logarithmic scale vertically, the curve becomes a straight line. This transformation reveals the underlying linear relationship in the exponents. Many natural phenomena that appear curved on normal plots appear perfectly straight when plotted logarithmically, which is how scientists confirm that certain phenomena truly follow exponential patterns. The concept of compounding frequency in finance illuminates how the rate of exponential growth depends on how often growth is calculated. If you earn annual interest at a percentage rate, your money grows exponentially with that compounded frequency. If you earn the same annual percentage, but it's compounded quarterly, you earn slightly more because each quarter's interest starts earning interest itself sooner. Monthly compounding earns more still. Daily compounding earns even more. The limiting case, continuous compounding at the same rate, produces the special number e at its heart. Building intuition for exponential functions involves recognizing them in unexpected places. The brightness of the night sky follows an exponential relationship with distance from Earth. It fades exponentially, not linearly. The intensity of light passing through a translucent medium follows an exponential decay. The probability of a randomly selected piece of data being exactly within a certain range follows an exponential distribution for some types of data. The strength of connections between neurons and learning systems follows exponential patterns. Musical notes follow an exponential relationship in frequency. Each octave higher doubles the frequency, so frequencies climb exponentially as you ascend the musical scale. The transition from growth dominated by one process to growth dominated by another often involves exponential behavior. When you turn on a light bulb, the brightness doesn't reach full intensity instantly, but grows exponentially toward it, following the time constant of the electrical system. When you apply a force to start moving an object through a resistant medium, the speed accelerates, but eventually plateaus, as the resistance balances the driving force, with the approach to terminal velocity following an exponential curve. When a new technology is adopted by a population, it often follows an S-curve, which is actually two exponential behaviors joined together. First, exponential growth as innovation spreads, then exponential saturation as the market becomes filled. The mathematics of exponential equations with different bases reveals how the base determines the speed of growth. A base slightly larger than 1 produces slow growth. A base of 2 produces growth that's noticeable but not dramatic. The base of 10 produces growth that's dramatic and rapid. The base determines everything about how the process unfolds over time. This is why scientists and engineers talk about orders of magnitude. Multiplying by 10 repeatedly represents exponential growth with base 10. Exponential equations appear frequently in physics, particularly in phenomena involving waves and oscillations. The amplitude of a damped oscillation, where a bouncing object gradually comes to rest due to friction or air resistance, follows exponential decay, multiplied by a periodic function. The result is a wave that oscillates while gradually diminishing in size, crossing the center line fewer and fewer times, until it effectively comes to rest. This behavior describes everything from a swinging pendulum, slowing down, to the vibrations of a struck drum fading away. The concept of equilibrium in systems involving exponential processes often involves finding a steady state where growth and decay balance. A bathtub filling from a faucet while draining from the bottom will reach an equilibrium, where the rate of water entering equals the rate of water leaving, creating a stable water level that remains constant over time. The approach to equilibrium often follows exponential behavior, getting closer and closer, but taking longer and longer to fully arrive. Understanding negative exponents provides insight into reciprocals and decay. Raising a base to a negative exponent is equivalent to taking the reciprocal and raising it to the positive exponent. If something grows by a factor of 2, then going backward in time by the same period means it was half as large. If you raise 2 to the 5th power, you get 32. Raising 2 to the negative 5th power gives you 1/32. This symmetry between growth and decay reflects the fundamental reversibility of exponential relationships. The intersection of exponential refunctions reveals important behaviors. Two exponential functions with different bases and rates will eventually cross at certain points. An exponential that starts small, but grows quickly, will eventually overtake one that starts large, but grows slowly. The time at which this crossover happens can be calculated by setting the two expressions equal and solving for the time variable, using logarithms to extract the answer from the exponential relationships. Real-world forecasting often relies on fitting exponential models to observe data and extrapolating into the future. A company tracking sales revenue, or a health agency tracking disease cases, or an environmental scientist tracking atmospheric carbon dioxide concentrations, all might fit exponential models to their data. The quality of these forecasts depends crucially on whether the underlying process truly follows an exponential pattern, and whether the conditions that produce that pattern remain stable. When exponential models are applied to inherently limited systems, they inevitably fail, as the exponential growth hits real-world constraints. The mathematics of epidemic modeling extends the simple exponential growth model to include recovery and immunity. The SEER model, for instance, divides a population into those who are susceptible, exposed, infected, and recovered. The movement between these categories follows differential equations that include exponential terms. The interplay between transmission and recovery rates determines whether an epidemic grows exponentially, stays steady, or shrinks exponentially. Teaching someone to think about exponentials means helping them develop intuition for how processes that compound grow deceptively quickly. A savings account with compound interest, a technology adoption curve, a population of reproducing organisms, a pandemic spreading through a naive population, a rumor traveling through a social network. These all start innocuously, and then explode into visibility once the exponential growth becomes large enough to notice. The half-life concept extends beyond. Radioactivity to any process where something decreases by half regularly. If you take a medication with a half-life of 6 hours, after 6 hours you have half the original amount in your bloodstream. After 12 hours, a quarter. After 18 hours, an eighth. This is why medications need to be taken regularly. The amount in your body is constantly decreasing exponentially, and you need to add more to maintain a therapeutic level. The exponential function with base e appears so frequently in calculus, because differentiation and integration treat it specially. Taking the derivative of e raised to a power produces the original function back, multiplied by that power. Taking the integral produces a similar result. No other base has this clean property, making the natural choice for continuous processes, and for the foundational mathematics that describes change. Consider mixing two liquids at different temperatures. The temperature difference between them decreases exponentially over time. The rate of cooling or heating is proportional to the temperature difference, so the remaining difference shrinks faster when the temperatures are far apart, and slower when they're close. This is Newton's law of cooling, and it's fundamentally an exponential process. A cup of coffee cools according to this law, with the temperature difference between the coffee and room temperature decreasing exponentially. The logistics of exponential growth describes how population growth, constrained by limited resources, can be modeled. Initially, when resources are abundant, growth is nearly exponential, but as the population approaches the carrying capacity of its environment, growth slows. The logistic equation combines exponential growth with a limiting factor proportional to how close the population is to its maximum, producing an S-shaped curve that starts with exponential growth, transitions to slower growth, and eventually plateaus. Compound interest calculations demonstrate how exponentials dominate over time. A small percentage difference in annual returns compounds into enormous differences over decades. An investment returning 5% annually versus one returning 6% annually seems like a small difference, just 1 percentage point. But over 30 years, the compounding effect means the 6% investment is worth significantly more. Over 60 years, the difference is dramatic. The exponential nature of compounding means that small differences in growth rates create large differences in outcomes when given sufficient time. The concept of doubling time versus multiplication factor represents two ways of understanding the same exponential process. A population growing at 10% annually will double in about 7 years. Describing growth in terms of doubling time gives a more intuitive sense than saying the growth rate is 10%. Similarly, the quantity decreasing at 10% annually will halve in about 7 years. These round numbers make it easier to reason about exponential processes without engaging directly with the mathematics. Exponential distribution and probability describes waiting times between events that occur randomly, but at a constant average rate. The time until the next meteor impact, the time until the next customer arrives at a store, the time until the next earthquake. These follow exponential distributions. The probability of waiting longer than a certain time decays exponentially. The probability of waiting exactly a specific time is 0, but the probability of waiting between two specific time is determined by integrating the exponential probability density function. The sensitivity of exponential processes to initial conditions and growth rate emphasizes why these functions are so important in modeling uncertainty. A tiny difference in growth rate produces vastly different outcomes over time. A tiny difference in initial value produces a proportional difference. This is why precise measurement through forecasting become increasingly important in systems governed by exponential processes. Power towers and tetration extend the concept of repeated multiplication to repeated exponentiation. 2 to the power of 2 is 4. 2 to the power of 2 to the power of 2 is 2 to the power of 4, which is 16. 2 to the power of 2 to the power of 2. 2 to the power of 2 is 2 to the power of 16, which is 65,536. These rapidly explode to unimaginably large numbers, demonstrating how exponentiation itself grows exponentially. The exponential function serves as a bridge between discrete processes and continuous processes. If something grows by a factor of 2 every year, that's discrete exponential growth. If something grows continuously at a rate proportional to its current size, that's continuous exponential growth. The exponential function of base e unifies these perspectives, showing how discrete compounding at increasingly frequent intervals approaches continuous compounding. In conclusion, exponential functions describe processes where growth or decay is proportional to the current state. They appear throughout nature and human systems because they emerge naturally whenever the rate of change depends on the amount present. Understanding them requires both mathematical facility and intuitive grasp of how things that compound become dominant forces in systems over time. The processes governed by exponentials feel deceptive to human perception, starting small and manageable, then suddenly revealing their unstoppable momentum. This quality makes them both fascinating and crucial to understand. When we speak of exponential behavior, we're really talking about a kind of growth that spirals outward in ways that defy our everyday intuition. Most of our experience involves linear thinking, where doubling your effort doubles your result, or adding more time to a project adds proportionally more value. But exponentials work in a fundamentally different language altogether. The heart of this language begins with a simple idea that somehow contains infinite complexity within it. Imagine you have a quantity, any quantity at all. Now imagine that this quantity grows not by a fixed amount, but by a percentage of itself. That percentage, applied consistently, creates something remarkable. It creates a curve that whispers upward at first, so gently you might not notice it's there, and then suddenly surges with a power that seems almost impossible. Let's think about what happens when something doubles repeatedly. If you start with 1 and keep doubling, you get 1, then 2, then 4, then 8, then 16, and so on. After 10 doublings, you've reached just over 1,000. After 20 doublings, you've passed 1,000,000. After 30 doublings, you're well beyond 1,000,000,000. The number of doublings grows arithmetically, but the value grows with astonishing speed. This is the essence of exponential behavior, and it's woven into the fabric of how the world actually works. Consider bacterial growth in a petri dish. A single bacterium doesn't just sit there producing one new bacterium per unit of time. Instead, when conditions are right, it divides into 2. Each of those divides into 2 more. Each of those into 2 again. Within hours. From a single invisible speck, you can have millions. The population doesn't increase by the same amount each time period. It multiplies by the same factor each time period. This multiplication is what makes exponentials so profoundly different from addition. There's a special number that sits at the very center of all exponential behavior in the universe. It's called E, and it equals approximately 2.71828. This number appears almost everywhere in nature, from the spiral of a nautilus shell to the distribution of galaxies across space, to the rate at which heat dissipates from a cooling cup of tea. It's not something humans invented for convenience. It's something we discovered embedded in the structure of reality itself. The reason E is so special has to do with what happens when you let compounding happen continuously, rather than in discrete steps. Imagine you have 1 unit of money in an account that earns 100% interest per year. After 1 year, you have 2 units. But what if that interest compounds twice a year instead, at 50% each time? After the first 6 months, you have 1.5 units. After the second 6 months, you have 1.5 times 1.5, which is 2.25 units. That's more than you get with annual compounding. What if interest compounds 4 times a year? Then each quarter you multiply by 1.25, and you end up with approximately 2.44 units. As you let the compounding happen more and more frequently, the final amount approaches a limit. That limit is E. This number E is the ultimate rate of continuous growth. It's what you get when you let a process compound at every infinitesimal instant. It's the answer to the question, what is the natural way things grow when they're left to themselves? Now, when we talk about exponential functions in general, we're talking about functions of the form where a base number gets raised to a power that contains a variable. The most important exponential function is where E is the base. If we let the variable be called x, then we're looking at e raised to the power x. This function has the remarkable property that its rate of change at any point is exactly equal to its value at that point. In other words, the faster it's growing, the more it grows. The growth feeds itself. The inverse of exponential growth is logarithmic growth. If you ask yourself the question, to what power must I raise e to get a particular number? The answer is the natural logarithm of that number. Logarithms compress exponential curves into linear ones. They're the mathematical way of asking, how many doublings does this take? How many times do I need to multiply by the same factor to reach this point? They're invaluable for understanding exponential processes, because our brains are wired to think logarithmically about many things. When we listen to music, our ears perceive loudness logarithmically. The difference between a whisper and normal speech is much smaller than the difference between normal speech and a shout. But our ears perceive them as roughly equal differences in loudness. Exponential growth and exponential decay are really two sides of the same coin. Decay happens when you have a base between 0 and 1. Radioactive substances don't lose a fixed amount of their mass each year. Instead, they lose a fixed fraction of what remains. Plutonium, with a half-life of 24,000 years, means that after 24,000 years, half of any amount you started with will have decayed. After another 24,000 years, half of what remained will decay, leaving you with a quarter of the original. The amount remaining after any time period follows an exponential decay function. It falls towards zero asymptotically, meaning it gets closer and closer to zero, but never quite reaches it. The mathematics here involves something called the exponential constant, raised to a negative power. If growth involves e to the positive x, decay involves e to the negative x. The negative sign flips the curve. Instead of shooting upward to infinity, it approaches zero. Instead of compound growth feeding on itself, compound decay diminishes with each step. A material losing half its substance, repeatedly, undergoes exponential decay. Your body's ability to metabolize caffeine follows exponential decay. The concentration of a drug in your bloodstream decreases exponentially over time, as your liver and kidneys process it. This connects to something called the half-life, which is fundamental to understanding how substances behave in the world. Every radioactive material, every medicine, every contaminated area has a characteristic half-life. Knowing this single number lets you calculate how much will remain after any period of time. Carbon-14 has a half-life of 5,700 years, which is why it's so useful for dating archaeological artifacts. Certain isotopes have half-lives of microseconds. Others have half-lives measured in billions of years. The exponential decay formula works the same way for all of them. When we move from simple doubling or halving to more complex scenarios, we need to think about growth rates expressed as percentages or proportions. An investment that grows at 5% per year doesn't grow by exactly the same amount each year. Instead, each year, you multiply the previous year's value by 1.05. After 1 year, you have 1.05 times your starting amount. After 2 years, you have 1.05 times 1.05, which is 1.1025 times your starting amount. After 10 years, you've multiplied by 1.05, raised to the 10th power, which is approximately 1.629 times your starting amount. The exponent is the time period, and the base is 1 plus the rate of growth. This principle scales to any growth rate. The population growing at 3% per year multiplies by 1.03 each year. The virus spreading through a population where each infected person infects 2 others on average has a doubling rate, meaning the base is 2. The time it takes for something to double when growing at a particular rate is called the doubling time. And there's a simple approximation for it. Divide 70 by the percentage growth rate. If something grows at 7% per year, it doubles in roughly 10 years. If it grows at 1% per year, it doubles in roughly 70 years. This little rule of thumb, sometimes called the rule of 70, captures the essence of exponential growth in a way that's easy to remember and applies across wildly different contexts. The power of exponential thinking becomes clear when you consider what happens over long time periods. A penny invested at an extremely high return rate of 30% per year, compounded annually, would become about $1 after 10 years, $10 after 20 years, $100 after 30 years, and over $1,000 after 40 years. But these numbers are still small, because the base is just 1.3. Now imagine a base of 2, representing a doubling each period. 1 becomes 2, then 4, then 8, then 16, then 32, then 64, then 128, then 256, then 512, then just over 1,000. After just 10 periods you've multiplied by 1,000. After 15 periods, you've multiplied by 32,000. After 20 periods you've multiplied by 1,000,000. This is why exponential growth is so dangerous, so powerful, so relevant to everything from pandemic spread, to climate change, to the growth of computational power. There's a story often told about the inventor of chess and the king of India. The inventor asked for a reward. A single grain of rice on the first square of the chessboard, 2 grains on the second square, 4 grains on the third square, and so on, doubling with each square. There are 64 squares. By the time you reach the last few squares, you're talking about more rice than was harvested in human history. The doubling starts innocuously. The first few squares contain hardly anything, but by the time you're halfway through the board, things have gotten serious. By the end, the numbers are incomprehensibly large. This story captures something true about exponential processes. They seem manageable, even trivial, until they're not. The same principle applies to compound interest in personal finance. A person who starts investing $100 per month at age 25 and achieves a 7% annual return will have significantly more money by retirement than a person who waits until age 35 to start and invests the same amount. The difference isn't just the extra 10 years of contributions, though that matters. It's the extra 10 years of exponential growth on money that was invested earlier. The money invested at 25 has 30 or 40 years to compound. The money invested at 35 has only 20 or 30 years. In exponential systems, starting early is disproportionately powerful. Understanding exponential growth is essential for thinking clearly about the future. Technological progress often follows exponential patterns. The number of transistors on a computer chip has roughly doubled every 2 years for decades, the pattern called Moore's Law. This exponential improvement in computing power underlies the entire digital revolution. Internet usage, the adoption of mobile phones, the spread of renewable energy technologies, all of these follow exponential curves at certain stages of their development. Someone who thinks linearly about these trends will systematically underestimate how fast things will change. But exponential growth cannot continue indefinitely. This is where understanding the limits of exponential functions becomes crucial. In the real world, exponential growth always bumps up against constraints. The bacterial colony grows exponentially until the nutrients in the petri dish run out. A virus spreads exponentially until enough people have been infected that the spread slows. The technology adoption curve rises exponentially at first, but eventually slows as it approaches saturation. The curve that describes this kind of constrained growth is called a logistic curve, and it looks like an exponential curve that's been stretched and flattened at the top, approaching a maximum value asymptotically. The logistic function is one of the most important mathematical models in biology, ecology, economics, and epidemiology. It captures the reality that growth is fast when you're far from the limit, but slows down as you approach it. A population in a limited environment follows a logistic curve. The number of people who adopt a new technology follows a logistic curve. The spread of a disease through a population follows a logistic curve. The curve starts slow, accelerates exponentially through the middle phase, and then slows as it approaches the upper limit. The inflection point, where growth transitions from accelerating to decelerating, occurs at exactly half the maximum value. Exponential thinking also applies to how problems compound. If you ignore a small problem, it often grows exponentially. A small cavity in a tooth, left untreated, can become a root canal, then an extraction, then an infection spreading through the jaw. A small crack in a relationship, left unaddressed, can grow into resentment and distance that becomes exponentially harder to repair the longer it persists. A small ecosystem imbalance can cascade exponentially into a collapse. Our intuition often fails us here because we're used to linear accumulation. We expect small problems to stay small. But exponential systems don't work that way. The mathematics of exponential equations opens up a whole world of solving problems we encounter in nature. When you have an exponential function, and want to find when it reaches a certain value, you use logarithms to solve for the variable in the exponent. If you know that a substance decays according to an exponential function, and you measure how much remains, after a certain time, you can use the data to determine the decay constant, and predict how much will remain in the future. If you know the growth rate of a population, you can predict when it will reach a certain size. These calculations depend on the deep relationship between exponentials and logarithms, where one undoes what the other does. There's also something called the exponential distribution, which describes the time between random events. If you have a process where events occur randomly at a constant average rate, the time you have to wait for the next event follows an exponential distribution. This applies to radioactive decay, to the timing of earthquakes, to the arrival of customers at a service counter, to the lifetimes of electronic components. The probability of having to wait longer than a particular time decreases exponentially. This means there's always a small but non-zero probability of waiting much longer than average. Some customers will arrive very shortly after the previous one. Others will have to wait a long time. The exponential distribution captures this variability precisely. When you move into higher mathematics and calculus, exponential functions become even more central. They're the only functions that are their own derivatives, meaning the rate of change of an exponential function equals the function itself. This property makes them fundamental to solving differential equations, which describe how systems change over time. Any system where the rate of change of a quantity is proportional to the quantity itself will be described by an exponential function. Heat dissipation, population growth, radioactive decay, chemical reactions, compound interest, the spread of rumors, the decline of a species toward extinction, all of these are described by exponential functions because in each case, the rate of change is proportional to the current amount. Complex exponentials, where the exponent is an imaginary number, connect exponential functions to trigonometric functions like sine and cosine. This connection, expressed in Euler's famous formula, is one of the most beautiful relationships in mathematics. It shows that complex exponentials spiral around in circles in the complex plane. This has profound applications in physics, engineering, and signal processing. Waves, oscillations, and vibrations can all be understood through the lens of complex exponentials. The mathematics of alternating current electricity, of quantum mechanics, of how electromagnetic waves propagate through space, all depend on understanding complex exponentials. The exponential map in dynamical systems reveals how sensitive systems can be to initial conditions. If you have a system where the next state depends on the current state in a particular way, and you look at two slightly different initial conditions, they will diverge exponentially. This is the mathematical heart of chaos theory. It's why weather is predictable for a few days, but not for months. It's why you can't know the position and momentum of a particle with perfect precision in quantum mechanics. It's why small perturbations in the orbits of planets can lead to dramatically different configurations over geological timescales. The exponential divergence of nearby trajectories defines chaotic systems. There's also the concept of exponential moving averages, which smooths data that fluctuates randomly. Instead of taking a simple average of all previous data points equally, an exponentially moving average gives more weight to recent data points, and exponentially less weight to older data points. This is used in finance to identify trends, in statistics to forecast future values, in engineering to filter out noise from sensors. The parameter that controls how much weight goes to recent data determines the timescale of the smoothing. In information theory and entropy, exponential functions appear when calculating probabilities in information content. Probability of a sequence of independent events is the product of the individual probabilities, which often leads to exponential functions in the exponent. This is why the normal distribution, so fundamental to statistics, has a Gaussian curve that's an exponential function of a squared term. The bell curve shape that describes measurement errors, heights, test scores, and countless natural phenomena is fundamentally exponential. Network effects and cascading failures both involve exponential dynamics. When a computer virus spreads through a network, or when a bank run develops during a financial crisis, or when a power grid failure cascades into a wider blackout, the spread follows exponential growth in the early stages. Conversely, when a network reaches a critical density, or a sufficient majority, adopts a new standard, benefits accrue exponentially. The value of a telephone network is roughly proportional to the square of the number of people connected to it, which is a kind of exponential effect in network systems. The exponential function also appears in chemistry and materials science. The rate of a chemical reaction depends exponentially on temperature through the Arrhenius equation. This is why chemical reactions happen so much faster at higher temperatures. Doubling the temperature doesn't double the reaction rate. Instead, the rate might increase by a factor of 2 to 10 or more. This exponential dependence on temperature is why we refrigerate food to preserve it, why enzymes in our bodies work optimally at a narrow temperature range, why industrial chemical processes are so sensitive to temperature control. In biology, allometric scaling laws often follow exponential relationships. The metabolic rate of an organism doesn't scale linearly with its size. Smaller animals have higher metabolic rates per unit of body mass. The relationship between metabolic rate and body mass follows a power law that's closely related to exponential functions. Affects everything from how often an animal needs to eat to its lifespan, to the speed at which it can move. Understanding these exponential relationships helps us understand why a shrew must eat nearly constantly to survive, while an elephant can go without eating for days. The exponential growth of human population is perhaps one of the most consequential exponential trends in human history. For most of human existence, population grew very slowly. Then, with agriculture, it began to grow faster. With industrialization and modern medicine, it accelerated dramatically. The world population doubled from about 1.5 billion in 1900 to about 3 billion in 1960, then doubled again to about 6 billion by 2000. The growth rate has actually slowed in recent decades, meaning we're transitioning from exponential to logistic growth. But the momentum of exponential growth in the 20th century fundamentally transformed human civilization, enabling the expansion of agriculture, industry, and consumption that characterizes the modern world. Energy consumption, carbon emissions, and resource extraction have all grown roughly exponentially with population and economic development. The concentration of carbon dioxide in the atmosphere has increased exponentially, following the exponential growth of fossil fuel consumption. This exponential increase in atmospheric carbon is driving exponential increases in global temperature, which in turn drives exponential increases in the frequency of extreme weather events. Understanding these exponential trends is crucial for thinking clearly about climate change and its trajectory. In physics, the exponential decay of unstable particles is described by quantum mechanics. A radioactive nucleus will decay at a rate determined by the weak nuclear force, but individual nuclei decay at unpredictable times. When you have a huge number of nuclei, their collective decay follows an exponential curve, with remarkable precision. This exponential behavior of quantum systems has been verified to extraordinary accuracy in laboratory experiments. It's one of the most fundamental patterns in nature. Exponential functions also appear in the mathematics of probability and likelihood. The likelihood of a particular sequence of outcomes decreases exponentially as the sequence gets longer if each outcome is unlikely. The probability that a randomly generated sequence of letters spells a meaningful word decreases exponentially with the length of the sequence. The probability of a quantum system remaining in a particular state decreases exponentially over time if that state is unstable. These exponential decay of probabilities are why impossible events with non-zero probability remain essentially impossible for all practical purposes. The concept of the Poisson distribution, fundamental to modeling random arrivals and occurrences, is intimately connected to exponential functions. The number of events occurring in a fixed time interval, when events occur at random at a constant average rate, follows a Poisson distribution. The shape of this distribution has an exponential term in its formula. This distribution applies to everything from the number of mutations occurring in a DNA sequence, to the number of cars arriving at a toll booth in an hour to the number of hits on a website in a day. In optimization problems, exponential functions often arise when considering the computational complexity of algorithms. Some problems can be solved in polynomial time, meaning the time required grows as a polynomial function of the input size. But other problems seem to require exponential time, meaning the time required grows exponentially with the input size. This is the distinction between problems considered tractable and those considered intractable. A problem that requires 2 to the power of n operations might be solvable for small n, but becomes impossible for large n. Why encryption relies on problems that are easy to verify, but exponentially hard to solve. The exponential time limit is also relevant to quantum computing. Classical computers can try solutions one at a time, so hard problems require exponential time. Quantum computers can exploit superposition to try many solutions simultaneously. This doesn't make all hard problems easy, but it does make some exponentially hard problems tractable. This is both the promise and the profound implication of quantum computing for cryptography and information security. In biology and evolution, exponential growth rates determine whether populations expand, stabilize, or decline. A population will grow if each individual produces more than one offspring on average, and the growth rate depends on the reproduction rate raised to the power of the number of generations. A small difference in the average number of offspring per individual, when raised to the power of many generations, can determine whether a species thrives or vanishes. This is the mathematical basis for natural selection and evolutionary dynamics. The concept of the net reproductive rate, which measures the average number of daughters a woman produces in her lifetime, determines whether a human population grows or shrinks. If each woman produces on average more than one daughter who survives to reproductive age, the population grows exponentially. If each woman produces on average less than one, the population shrinks exponentially. In developed countries, fertility rates have fallen below replacement level, meaning populations would decline exponentially without immigration. In developing countries, high fertility rates still drive exponential growth. The global population trajectory depends on how quickly fertility rates converge across different regions. Exponential functions also appear when analyzing the stability of equilibrium points in dynamical systems. A system in equilibrium will either return to that equilibrium or diverge away if it's slightly perturbed. The rate at which it returns or diverges involves exponential functions. A stable equilibrium has solutions that decay exponentially back to the equilibrium. An unstable equilibrium has solutions that grow exponentially away from it. This exponential stability analysis is used throughout engineering and physics to understand whether systems are safe and controllable. The exponential distribution of income and wealth, often called the Pareto distribution or power law, shows that wealth is distributed very unequally across populations. A small percentage of the population controls a large percentage of the wealth. This isn't random. It emerges naturally from processes where wealth generates wealth exponentially. If your wealth earns returns, and those returns are reinvested, your wealth grows exponentially. Small differences in initial wealth compound exponentially. Over time, small disparities become vast ones. In signal processing and telecommunications, exponential functions describe how signals decay or amplify as they travel through systems. The intensity of light traveling through water decreases exponentially with depth, because water absorbs light. The amplitude of sound waves traveling through fog decreases exponentially with distance. These exponential decays determine how far signals can propagate before becoming too weak to detect. This is fundamental to designing communication systems, medical imaging, and any technology that relies on detecting signals in the presence of losses. The mathematics of epidemic control relies on exponential growth in the early phase. The basic reproduction number, denoted R0, represents the average number of people an infected person will infect. If R0 is greater than 1, the number of infected people grows exponentially. Each generation of infections is R0 times as large as the previous generation. If R0 is less than 1, the epidemic dies out exponentially. The difference between R0 of 1.1 and 1.2 might not seem large, but when raised to the power of many generations, it determines whether an epidemic remains controllable or explodes into a catastrophe. Understanding the transition from exponential growth to slower growth modes is crucial for public health. When a disease first appears in a population, it spreads exponentially because almost everyone is susceptible. As more people are infected and develop immunity, the effective reproduction number decreases. Eventually, the disease reaches a phase where it's no longer growing, but fluctuating around an endemic level. Some diseases, like smallpox, can be driven to extinction if vaccination rates are high enough to bring the reproduction number below 1. Others persist, oscillating between seasons of high transmission and low transmission. In summary, exponential functions are not merely mathematical abstractions. They are the language in which nature describes processes of growth, decay, compounding, and change. From the tiniest atomic nuclei to the largest structures in the universe. From the behavior of money and bank accounts to the spread of ideas through society, exponential functions appear. They describe how quantities that feed on themselves grow, and how quantities that diminish with what remains decay. They connect to logarithms in a deep partnership, where one function undoes what the other does. They ground our understanding of probability, stability, complexity, and the fundamental dynamics of how the world works. The intuition for exponential behavior doesn't come naturally to humans, because we evolved in environments where most phenomena were roughly linear. But the modern world is filled with exponential dynamics. Digital technology, climate change, financial markets, disease spread, information networks, all of these are fundamentally exponential in nature. Developing intuition for exponential growth and decay is perhaps one of the most valuable intellectual skills for understanding the contemporary world and the futures we might face. The power of exponential thinking is that it allows us to see patterns across vastly different scales and contexts. A pandemic, a viral video, the financial bubble, a species invasion, a technological innovation, all of these share common exponential dynamics in their early stages. The mathematics that describes one describes all of them. This universality of exponential behavior, this way that different systems follow the same mathematical laws, reveals something profound about the structure of reality itself. Nature solves similar problems with similar solutions, and one of nature's favorite solutions is the exponential function. The chamber had grown quieter now, the earlier revelations settling into something more contemplative, as the crystalline formations along the walls pulsed with that familiar rhythm of accumulated understanding. Kira found herself drawn to a section of the archive she hadn't noticed before, where the light seemed to fold inward on itself, creating pockets of concentrated brilliance that reminded her of stars collapsing into their own density. Theron was already there, his fingers tracing patterns in the air that left trails of phosphorescent residue. Equations made visible in the substance of the space itself. He didn't look up when she approached, but his voice carried that quality of someone continuing a conversation that had never really paused. The problem with teaching growth, he said, is that we keep trying to make it gentle when the truth is that nature has never been interested in gentleness. It's interested in efficiency, in the kind of accumulation that doesn't apologize for its own magnitude. Kira settled onto a formation that had shaped itself into something like a seat, its surface warm against her despite the crystalline appearance. She watched the trails his fingers left, trying to read them before they faded. "What are you drawing?" she asked. "Not drawing. Remembering. There was a time when I thought that repeated multiplication was the most violent thing mathematics could do. Take a number and fold it over itself again and again, watching it explode past any reasonable boundary. But then I understood that violence is the wrong word entirely. It's more like," he paused, searching, "like watching something finally become what it was always meant to be." The archive seemed to respond to his words, shifting its illumination so that certain formations caught the light more brightly than others. Kira had learned to read these responses, understanding that the space itself was participating in the lesson, highlighting elements it deemed relevant. "Talking about powers," she said. "About what happens when multiplication stops being content with pairs." Theron finally looked at her, and there was something in his expression that suggested approval tinged with caution. "I'm talking about transformation, about the difference between adding something to itself and multiplying something by itself. Both involve repetition, but they create entirely different kinds of change." He gestured, and the phosphorescent trails rearrange themselves into a simple pattern. If I take a number and add it to itself 3 times, I get something comprehensible. Take 2, and add it to itself, so that we have 2 plus 2 plus 2, and we arrive at 6. Pleasant. Manageable. The kind of growth that doesn't startle anyone. The pattern shifted, the trails folding into a tighter configuration. But if I take that same 2, then multiply it by itself 3 times, creating what we call 2 raised to the 3rd power, suddenly we have 8. From the same number, the same count of repetitions. But now we've crossed into territory that moves faster, reaches further. Kira nodded slowly. The archive's formations were pulsing more rapidly now, responding to the escalating concepts. I've seen this before. In the outer reaches, there's a pattern the crystalline structures make when they're storing information about populations, about how things grow over time. Exactly, Theron said. Because populations don't add. They multiply. Each generation doesn't contribute a fixed amount to the total. It contributes a proportion of itself. And proportion applied repeatedly is precisely what powers describe. He began to pace, his movements stirring currents in the illumination that surrounded them. Consider what happens when we examine specific cases. When we say that a number is raised to the 2nd power, we're describing that number multiplied by itself exactly once. 5 in the 2nd power means 5 multiplied by 5, giving us 25. Simple. Enough. Almost innocent. The trails were formed into a square shape, and Kira understood immediately why the 2nd power was often called squaring. The geometry was literal. A figure with equal sides, its area representing the product of its dimensions. The move to the 3rd power, Theron continued, and something shifts. Now we have 5 multiplied by itself, and then multiplied by itself again, creating 5 times 5 times 5, which yields 125. The square has become a cube, the flat has gained depth, and our number has leaped from 25 to 125, in what appears to be a single step. The crystalline formations around them seemed to vibrate at a frequency just below hearing, and Kira felt the resonance in her chest. This is what the builders were trying to encode. She realized. Not just how to calculate these things, but why they matter. Why this particular pattern of repetition creates results so different from simple addition. Theron nodded, his expression growing more intense. The builders understood that our intuition is calibrated for addition. We evolved counting steps, measuring distances, accumulating resources, 1 unit at a time. Our minds naturally expect linear progression, a steady climb of 1 more, and then 1 more again. But powers don't work that way, Kira said, finishing this thought. They curve upward, accelerating as they go. More than curve, Theron corrected. They escape. Watch what happens when we extend the pattern further. Let's take the number 2 and trace its powers upward. The phosphorescent trails rearranged into a vertical column, each level representing an increasing power. 2 to the 1st power is simply 2 itself, unchanged by the trivial act of appearing once. 2 to the 2nd power gives us 4. The number folded over itself once. 2 to the 3rd power produces 8. Then 2 to the 4th creates 16. And 2 to the 5th yields 32. He paused, letting the pattern establish itself. Notice how each step isn't adding the same amount. From 2 to 4, we gained 2. From 4 to 8, we gained 4. From 8 to 16, we gained 8. And from 16 to 32, we gained 16. The gains themselves are doubling, accelerating at the same rate as the original growth. Kira stood, moving closer to the display. That's why it feels like it's running away from you. Because the acceleration is itself accelerating. Every step forward creates larger steps for the future. The archive's formation suddenly flared brighter, and Kira felt rather than heard a low hum resonating through the crystalline structures. It was the sound of recognition, of a principle being properly understood for the first time. Theron smiled, a rare expression that transformed his usually severe features. Now you're beginning to see. But we've barely started. Let's continue the sequence, and watch what happens when we extend beyond these comfortable initial values. 2 to the 10th power, he said, his voice taking on a rhythmic quality, equals 1024. We've crossed into thousands from a mere 2, using only 10 repetitions of multiplication. 2 to the 20th power reaches 1,048,576. 20 repetitions have carried us past 1,000,000. The numbers hum in the air, trails of light that seemed almost too bright to look at directly. Kira found herself backing away instinctively, as though the magnitude itself posed some kind of physical threat. And 2 to the 30th power, Theron continued, produces 1,073,741,824. 30 repetitions. That's all it takes to leap from 2 to more than 1 billion. Do you understand now why the builders considered this the most important pattern to preserve? Kira turned slowly, taking in the transformed chamber. The crystalline formations had rearranged themselves during Theron's demonstration, and she could now see that they formed a kind of map, a representation of how these powers spread through the archive structure. They used it for storage, she said quietly. The way the data is organized here, it follows these same patterns. Each level of depth contains spaces proportional to powers of some base. Theron nodded approvingly. Very good. The builders understood that exponential organization could hold vastly more information than linear arrangements. A structure with 10 levels, where each level branches into 10 new paths, contains 10 to the 10th power possible locations. That's 10 billion unique addresses. From just 10 levels of organization. He moved to one of the larger formations, running his hand along its faceted surface. But they also understood the dangers. Powers that grow can consume resources faster than any linear process could hope to replenish them. They designed systems with deliberate constraints, knowing that unchecked exponential growth would eventually break any container. Kira thought about the failing sections of the archive, the areas where the crystalline structures had gone dark, or become corrupted. Some of those failures, she realized, might not have been random decay. They might have been the result of growth patterns that exceeded their boundaries, processes that doubled and doubled, until they shattered the frameworks meant to contain them. Tell me about the inverse, she said. If powers represent this kind of explosive growth, there must be something that works in the other direction. Theron's expression shifted to something more complex, a mixture of appreciation and wariness. Roots. The inverse operation of raising to a power is taking a root. And yes, they're just as fundamental. But they move in the opposite direction, from expansion back toward compression. He drew new patterns in the air, trails that curve downward rather than up. If we know that 8 is 2 raised to the way third power, then we can reverse this relationship, and say that 2 is the third root of 8. It's the number which, when raised to the third power, returns us to 8. The concept felt familiar to Kira, like something she had encountered before, but never quite internalized. So roots are asking a different question. Instead of asking what happens when we multiply a number by itself repeatedly, we're asking what number would produce a given result through repeated multiplication. Exactly. Theron's trails formed into branching patterns that resembled tree roots, sinking into soil. Consider the square root, the second root, the most familiar case. When we ask for the square root of 25, we're asking what number multiplied by itself gives 25. The answer is 5, because 5 times 5 equals 25. But the square root of 25 could also be negative 5. Kira interjected. Since negative 5 times negative 5 also equals 25. Theron paused, and his smile returned briefly. You've been studying on your own. Yes, every positive number has 2 square roots, one positive and one negative. By convention, when we speak of the square root, we usually mean the positive one, the principal root. But mathematically both exist, and this duality becomes important in more advanced applications. He resumed his pacing, the phosphorescent trails following him like loyal companions. Roots reveal something profound about the relationship between numbers. They show us that for every explosive expansion, achieved through powers, there exists a corresponding compression that can undo it. They're mathematical inverses, each one the reversal of the other. Kira watched the patterns interweave, expansion and compression dancing together in the archive's light. But they don't feel symmetric, she said. Powers feel violent, like you said earlier. Roots feel, she searched for the right word, cautious, like approaching something carefully rather than rushing toward it. Theron nodded. That asymmetry is real, not just emotional. Calculating powers is straightforward, mechanical even. Take a number, multiply it by itself the specified number of times, and you have your answer. But calculating roots, especially for numbers that don't have neat integer results, is far more complex. It often requires approximation, iteration, a gradual refinement toward an answer that may never be expressed exactly. He stopped near a formation that seemed older than the others, its crystalline surface marked with intricate patterns that looked almost like writing. The builders spent considerable effort developing methods for root extraction. Some of those methods are preserved here, algorithms that approach roots through repeated guessing and correction. Kira moved to examine the formation more closely. The patterns weren't exactly writing, she realized, but something more like diagrams. Flowcharts rendered in crystalline structure. Can you show me how one works? Theron considered for a moment, then traced a new pattern in the air. Let's say we want to find the square root of 2. We know this root exists because 2 lies between 1 and 4, and the square root of 1 is 1, while the square root of 4 is 2. So the square root of 2 must be somewhere between 1 and 2. The trails form a number line, with markers at 1 and 2. We begin by guessing. Let's try 1.5. We square this guess, calculating 1.5 times 1.5, which gives us 2 1/4. This is larger than 2, so our guess was too high. The marker adjusted, moving slightly downward. We adjust and try 1 4/10. Squaring this gives us 1 96/100, which is less than 2. Now our guess is slightly too low. The root lies between 1 4/10 and 1.5. Kira watched the convergence, the way the upper and lower bounds crept towards each other with each iteration. We keep narrowing, she said. Each calculation gives us better bounds, and eventually we can get as close as we need. Precisely. Theron's voice carried satisfaction at her understanding. We might continue to find that the square root of 2 is approximately 1.41421356, and we could extend this to any number of decimal places desired. But here's what the builders discovered and deemed essential to preserve. The square root of 2 is not a fraction. It cannot be expressed as one whole number divided by another. The formations around them flickered, as though this statement carried particular significance to the archive itself. Kira felt the shift in atmosphere, the way the crystalline structures seemed to pay closer attention. What do you mean it's not a fraction? She asked carefully. Every number can be written as a fraction, can't it? Even if it's just the number written over 1. Theron shook his head. There's a distinction here that the builders considered one of the most beautiful discoveries in all of mathematics. Whole numbers and fractions form what we call the rational numbers, quantities that can be expressed as ratios of integers. But the square root of 2 defies this classification. No matter how we search, we will never find two whole numbers whose ratio equals this root exactly. He traced a proof pattern in the air, and Kira recognized it as one of the ancient demonstrations, a method of showing that assuming the opposite leads to contradiction. The proof goes something like this. Suppose, for the sake of argument, that the square root of 2 could be written as a fraction in lowest terms, some whole number divided by another with no common factors between them. The trails formed into symbolic representations, relationships made visible. If this fraction, when squared, equals 2, then the first number squared must equal twice the second number squared. But this would mean the first number squared is even, which means the first number itself must be even, since odd numbers produce odd squares. Kira followed the logic, feeling the inexorable movement toward contradiction. If the first number is even, we can write it as 2 times some other whole number. Exactly. Theron's pattern grew more complex. Substituting this, we find that the second number squared must also be even, which means the second number must be even too. But now we have a contradiction. We assumed our fraction was in lowest terms, with no common factors, yet we've proven that both numbers must be divisible by 2. The assumption cannot hold. The patterns collapsed into a single point of light, the logical structure reducing to its inescapable conclusion. Therefore, Theron finished. The square root of 2 cannot be a fraction. It exists. It's a definite quantity with a precise location on the number line, but it lives outside the realm of ratios. The builders called such numbers irrational, not because they're crazy, but because they cannot be expressed as ratios. Kira sat down again, feeling slightly overwhelmed by the implications. So there are numbers that exist between fractions, quantities that no fraction can ever exactly equal? Infinitely many of them. Theron's voice was gentle now, understanding the vertigo that often accompanied this realization. In fact, there are more irrational numbers than rational ones, in a precise mathematical sense that involves comparing infinities. The number line is densely populated with these unratioable quantities, and powers and roots are one of the primary sources that generate them. The archive's illumination shifted again, this time towards warmer tones that seemed designed to ease the conceptual strain. Kira appreciated the adjustment, though she wasn't sure if it was Theron's doing, or the space's own intelligence responding to her state. Let's step back from pure abstraction for a moment, Theron suggested, and consider how these ideas apply to the world we can observe. Powers don't just appear in calculations. They describe real phenomena, processes that unfold according to the same mathematical patterns we've been exploring. He moved toward a different section of the archive, one where the crystalline formations seem more organic, less geometric. Consider how populations grow. Imagine a species where each individual produces 2 offspring. In the first generation, we have 1 individual. In the second, we have 2. In the third, 4. Then 8, then 16, then 32. The formations shifted to illustrate his words, shapes dividing and redividing in geometric progression. After 10 generations, we have 2 to the 10th power, which is 1024 individuals. After 20 generations, over a million. After 30 generations, more than a billion. Kira nodded. I've seen simulations of this in the outer archives, but they always include limiting factors, constraints that prevent the growth from continuing indefinitely. Because it must, Theron agreed. No physical system can sustain exponential growth forever. Eventually, resources run out, space fills up, or some other constraint imposes a ceiling. But the mathematical pattern underneath, the pure exponential, doesn't know about ceilings. It simply grows, and understanding that growth is essential to understanding why constraints become necessary. He gestured toward a formation that displayed what appeared to be historical records, crystalline layers representing different eras. The builders saw civilizations rise and fall, and they noticed that the falls often came when growth patterns exceeded sustainable limits. A society that doubles its resource consumption every generation cannot continue for many generations without crisis. Kira thought about this, connecting it to other patterns she had observed in the archive. Is that why so much of what they preserve focuses on balance? On systems that maintain equilibrium, rather than expanding forever? Partly. But they also preserve the growth patterns themselves, knowing that they were powerful tools when properly controlled. A process that grows exponentially can accomplish in 10 steps what linear processes would require 1,000 to achieve. The key is knowing when to apply such power, and when to restrain it. Theron moved back toward the main chamber, and Kira followed, sensing that they were transitioning to a new aspect of the lesson. The trails he had been drawing faded gradually, their luminescence returning to the ambient glow of the formations. Let's talk about the notation, he said, in a way that might seem less abstract. When we write that some quantity equals a base raised to an exponent, we're describing a very specific relationship. The base is what's being multiplied. The exponent tells us how many times, and the result is the power. He formed 3 distinct shapes in the air, representing each component. If we take 3 as our base and 4 as our exponent, we're saying 3 multiplied by itself 4 times. That's 3 times 3 times 3 times 3, which equals 81. The base, the exponent, and the power form a triad, any 2 of which can determine the third. Kira traced the relationship mentally. So if I know the power and the exponent, I can find the base by taking the appropriate root. 81 with a 4th root gives me 3. Correct. And if you know the power and the base, finding the exponent requires yet another operation, one we haven't discussed yet. Theron's expression grew thoughtful. This third operation is called the logarithm, and it completes the symmetry of exponential relationships. The term was unfamiliar to Kira, or at least she hadn't encountered it in her previous explorations. Logarithm, she repeated, testing the word. What does it mean? It means the question we're asking has shifted again. Theron drew new patterns, these ones spiraling inward rather than outward. Powers ask, if I multiply this base by itself this many times, what do I get? Roots ask, what base multiplied by itself this many times gives this result? Logarithms ask, how many times must I multiply this base by itself to reach this result? The spirals tightened, converging on a central point. Consider our example again. We know that 3 raised to the 4th power equals 81. The logarithm base 3 of 81 is asking, what power must I raise 3 to in order to get 81? And the answer is 4. Kira felt something click into place, a conceptual lock opening. So logarithms are another inverse, just viewed from a different angle. Exactly. Roots and logarithms are both inverses of exponentiation, but they invert different aspects. Roots find the base when you know the power and exponent. Logarithms find the exponent when you know the power and base. Together with exponentiation itself, they form a complete system, a triad of operations that can solve any question about multiplicative relationships. The archive's formations seem to resonate with this completeness, arrangements shifting to reflect the threefold symmetry Theron had described. Kira could see now how the builders had organized this section, each operational family represented in crystal structures that mirrored each other's forms. Why are logarithms less commonly known, she asked. Powers are everywhere. Roots show up in basic geometry. The logarithms seem more hidden. Theron considered the question carefully. Perhaps because they emerged later in mathematical history, or because their practical applications were more specialized. Logarithms became essential with the development of certain calculating devices, ways to transform difficult multiplications into easier additions. He drew a demonstration, 2 numbers represented as trails of light. Here's the remarkable property. The logarithm of a product equals the sum of the individual logarithms. If I want to multiply 2 large numbers together, I can find their logarithms, add those logarithms, and then reverse the process to find the product. The trails merged, their lengths adding while their luminosities combined. This seems roundabout, Kira observed, adding extra steps to avoid multiplication. Until you realize they're uncountered, that for centuries, computing logarithms once and recording them in tables was easier than performing fresh multiplications. Astronomers, navigators, and engineers all relied on logarithm tables to calculate quantities that would otherwise have taken hours of tedious arithmetic. The tables converted multiplication into addition, division into subtraction, powers into simple multiplication. Kira tried to imagine a world without the calculating abilities she took for granted, where every multiplication had to be performed by hand. The value of such tables would have been immense. The builders preserved some of these tables, Theron continued, pointing to a nearby formation that held what appeared to be dense numerical data. Not because they expected us to use them directly, but because they represent a particular moment in mathematical history, a time when humanity's relationship with calculation was mediated through these pre-computed references. Kira approached the formation, running her fingers over the crystalline surface. The data was organized in a pattern she could now recognize. Logarithms of successive numbers recorded with painstaking precision. How were these tables originally calculated, she asked. Through careful application of the properties we've discussed. Theron joined her at the formation. The logarithm of 1 in any base is 0, because any number raised to the 0 power equals 1. The logarithm of the base itself equals 1, because the base raised to the first power equals the base. From these anchor points, other values can be derived through the additive property and various mathematical techniques. He traced a path through the crystal. Theta, for example, once you know the logarithm of 2 and the logarithm of 3, you can find the logarithm of 6 by adding them, since 6 equals 2 times 3. The logarithm of 4 is twice the logarithm of 2, since 4 equals 2 squared. These relationships allowed mathematicians to build complete tables from relatively few initial calculations. The elegance of it struck Kira, the way a few basic principles could generate an entire reference work. It's like the archive itself, she said, built from simple rules that combine to create complexity. Theron nodded. The builders saw the same parallel. They designed this place to embody mathematical principles, to make abstract relationships concrete in crystalline form. The organization you observe here is not arbitrary. It follows the same patterns of multiplication and power that govern the quantities being stored. He stepped back, gesturing broadly at the surrounding structures. Each beta section branches into 10 subsections, representing multiplication by 10. Move 3 levels deep, and you've multiplied by 10 3 times, reaching 1,000. The address of any piece of information encodes its relationship to every other piece, to these exponential structures. Kira looked at the archive with new eyes, seeing the mathematical bones beneath its crystalline surface. And when sections fail, when corruption spreads, she began. It often propagates exponentially. Theron confirmed grimly. A single error in a branching point can cascade into 10 downstream locations, then 100, then 1,000. This is the danger of power-structured systems. Their efficiency is matched by their vulnerability to multiplicative failure. They stood in silence for a moment, contemplating this double-edged nature. The archive had clearly suffered such cascades at various points in its history, entire regions going dark as errors propagated faster than repair systems could contain them. Eventually, Kira spoke again. You mentioned that logarithms in different bases are related. Can you show me how that works? Theron's expression lightened, returning to the mode of instruction. Of course. This is another beautiful property that the builders considered essential. Logarithms in different bases are proportional to each other, connected by constant conversion factors. He drew parallel lines of light, each representing logarithms in a different base. Consider the logarithm base 10 of 100, which equals 2, since 10 squared is 100. Now consider the logarithm base 2 of 100, which is approximately 6.644, since 2 raised to this power approximates 100. The lines shifted, maintaining their parallel relationship, but at different scales. The ratio between these two logarithms is constant. It equals the logarithm base 2 of 10, approximately 3.322. This ratio allows you to convert any logarithm in one base to the equivalent logarithm in another base through simple multiplication. Kira worked through the implications. So if someone gives me a logarithm in base 10, I can find the corresponding logarithm in base 2 by multiplying by this constant factor. Exactly. And this universality is why certain bases became conventional. Base 10 logarithms, called common logarithms, were favored for everyday calculations. because they allied with our decimal number system. Base E logarithms, called natural logarithms, became essential in advanced mathematics because they arise naturally from calculus and continuous growth. The mention of E caught Kira's attention. She had encountered this constant before in other sections of the archive, a number approximately equal to 2.71828 that seemed to appear everywhere. Why does E appear in logarithms? She asked. Theron's smile returned, broader than before. That question leads to one of the deepest mysteries the builders chose to preserve. The number E is defined through a limiting process involving powers, and it turns out to be the base for which the rate of exponential growth equals the current amount at every instant. He traced a curve in the air, the distinctive shape of exponential growth. Imagine something growing so that its rate of increase is always exactly equal to its current size. If you have 10 units, you're gaining at a rate of 10 per unit time. If you reach 100, your rate becomes 100. This process, it turns out, to be described using E as the base. The curve continued, sweeping upward with increasing steepness. The function E raised to some power has the remarkable property that it equals its own derivative, its own rate of change. This makes it fundamental to any mathematics involving rates and changes, which includes much of physics, engineering, and the natural sciences. Kira stared at the curve, trying to grasp why this property was so significant. So here appears because it describes change in the most natural way possible? In some sense, yes. Theron's voice grew reflective. The builders spent considerable effort ensuring that the properties of Y were preserved here, not just its numerical value, but the various ways of deriving it, understanding it, applying it. They considered it one of the most important numbers in mathematics, alongside 0, 1, pi, and the imaginary unit. The imaginary unit, Kira repeated. You mean the square root of -1? Theron's expression became cautious. You're moving faster than I expected. Yes, that's what I mean. And the fact that these 5 numbers are connected by a single elegant equation was considered by the builders to be, perhaps, the most beautiful relationship in all of mathematics. Kira waited, sensing that he would reveal this equation when he was ready. The archive's illumination had shifted again, taking on an anticipatory quality, as though the crystalline structures themselves were aware of what was about to be discussed. The equation, Theron said slowly, is this. E raised to the power of I times pi plus 1 equals 0. He traced the relationship in the air, each component glowing with its own distinctive color. The base of natural logarithms. The imaginary unit, the square root of -1. The ratio of the circle's circumference to its diameter. The unit quantity. The absence of quantity. All connected in a single simple equation. Kira felt a sensation she couldn't quite name. Something between awe and vertigo. She struggled for words. That's impossible. How can the square root of -1 and the ratio of circles combine with the base of natural logarithms to produce such a clean result? It seems impossible, Theron agreed, because our intuition hasn't been trained for it. But the mathematics is rigorous, demonstrable, verified by multiple independent approaches. The builders considered this equation a kind of proof that mathematics isn't merely a human invention, but rather a discovery of relationships that exist independently of our minds. He let the equation hang in the air, its 5 components casting subtle shadows across the crystalline formations. We should explore how we arrive at this equation, he continued. It requires understanding what happens when we extend exponentiation beyond the familiar territory of positive whole numbers. Kira nodded, her earlier overwhelm having transformed into hungry curiosity. The foundations, she realized, had been laid carefully throughout their conversation, each concept building toward this moment of unexpected connection. Let's begin with negative exponents, Theron said, returning to the methodical tone of instruction. We've discussed what it means to raise a number to a positive power, multiplying it by itself repeatedly. But what could it possibly mean to raise a number to a negative power? He drew the now familiar pattern of 2 raised to successive powers. 2 to the third gives 8. 2 squared gives 4. 2 to the first gives 2. Now, notice what happens as we decrease the exponent by 1 each time. We divide by 2. 8 divided by 2 is 4. 4 divided by 2 is 2. The pattern extended, exponents decreasing through 0 and into negative territory. If we continue this pattern, 2 to the 0, power should be 2 divided by 2, which is 1. And 2 to the negative first power should be 1 divided by 2, which is 1/2. Kira followed the logic, seeing how it emerged naturally from the established pattern. So negative exponents represent division rather than multiplication. More precisely, they represent reciprocals. Theron's trails adjusted to illustrate. 2 to the negative first power is 1 divided by 2, or 1/2. 2 to the negative second power is 1 divided by 2 squared, or 1/4. 2 to the negative third power is 1 divided by 2 cubed, or 1/8. The reciprocal relationship was clear now, each negative power producing a fraction that decreased as the negative exponent grew in magnitude. It's the mirror image of positive powers, Kira observed. Where positive exponents create explosive growth, negative exponents create rapid decay towards zero. Precisely. And this decay follows the same mathematical rules as growth, just in reverse. This symmetry is essential to the full understanding of exponential relationships. Theron moved to a different formation, one that displayed continuous curves rather than discrete points. Now let's consider what happens between the whole numbers. What does it mean to raise 2 to the power of 1/2 or 3/2 or any fraction? Kira thought about it, connecting to their earlier discussion. 1/2 power should be related to the square root somehow. Exactly correct. He traced the relationship carefully. If we accept that the laws of exponents should hold for all powers, then 2 raised to 1/2, multiplied by itself, should equal 2 raised to the sum of those powers, which is 1. So 2 to 1/2 times 2 to 1/2 equals 2 to the first, which is just 2. The conclusion followed inexorably. Therefore, 2 to 1/2 is a number that, when squared, gives 2. That's the definition of the square root of 2. And 2 to 1/3 would be the cube root of 2. Kira continued. The number which, when cubed, returns 2. Yes. Fractional exponents are roots. The denominator of the fraction tells you which root. 2 to the 1/4 is the 4th root, 2 to the 1/5 is the 5th root, and so on. Theron's trails formed a continuous curve now, connecting all these discrete points into a smooth function. When we allow exponents to be any fraction, the exponential function becomes continuous. We can raise 2 to the power of 1.4142, or 3.7, or any value we choose. The function flows smoothly through all these points. Kira studied the curve, its shape now familiar, the characteristic exponential growth that started slow, and then accelerated dramatically. This must be how the function is actually defined, she realized. Not through discrete multiplication, but through this continuous extension. You're grasping something that took mathematicians considerable effort to formalize. Theron acknowledged. The rigorous definition of exponential functions for arbitrary exponents requires limits and continuity, concepts from calculus. But yes, the result is a smooth, continuous function that agrees with our intuitive notion of repeated multiplication, wherever that notion applies. He paused, gathering himself for the next step. Now we come to the truly strange territory. What happens when the exponent is not even a real number, but an imaginary one? The crystalline formations seem to darken slightly, not from any change in illumination, but from the sheer weight of the conceptual leap being attempted. Kira had encountered imaginary numbers before, knew that they were defined as multiples of the square root of -1, but she had never considered what it might mean to use them as exponents. This seems like it shouldn't be possible, she said carefully. Exponents have always represented some kind of multiplication, of repeated application. How can you apply something an imaginary number of times? Theron's response was gentle but firm. You're right that our intuition breaks down here, but mathematics doesn't require intuition to function. It requires consistency. And it turns out that extending exponentiation to imaginary powers in a consistent way leads to remarkable, verifiable results. He began to trace a new pattern, this one circular rather than linear. Consider what happens when we calculate e raised to an imaginary power. Let's take e raised to I times theta, where theta is some real number. The trails formed into a circle, points marked at regular intervals around its circumference. If we plot these values on what we call the complex plane, with real numbers running horizontally, and imaginary numbers running vertically, something beautiful happens. The points all lie on a circle of radius 1, centered at the origin. Kira stared at the circle, trying to understand why exponentiation would produce circular patterns. It seemed so arbitrary. Why would imaginary exponents create rotation? It's not arbitrary at all. Theron's voice carried conviction born of deep understanding. The connection arises from the fundamental properties of e and I, from the way the exponential function relates to trigonometric functions like sine and cosine. He traced the relationship explicitly. E raised to I times theta equals the cosine of theta, plus I times the sine of theta. This is sometimes called Euler's formula, after the mathematician who explored its implications most thoroughly. The exponential function with imaginary exponent produces a complex number whose real part is cosine, and whose imaginary part is sine. The crystalline formations shifted to display this relationship, sine and cosine curves interweaving with the circular pattern of the complex exponential. Kira could see the connections now, how the oscillating trigonometric functions combine to trace out a circle when viewed in a complex plane. And when theta equals pi, she said slowly, working through the implications, the cosine of pi is -1 and the sine of pi is 0. So e raised to I times pi equals -1 plus 0 times I, which is just -1. Exactly. Theron's smile was broad now, the smile of a teacher watching understanding dawn. And if e raised to I times pi equals -1, then adding 1 to both sides gives us e raised to I times pi plus 1 equals 0. The equation hung in the air again, but this time Kira saw the path that led to it, understood how each component contributed. The number e brought the properties of natural growth and the exponential function. The imaginary unit, I provided the rotation, the circular motion in the complex plane. The constant pi fixed the angle at exactly half a rotation, placing the result on the opposite side of the circle from where it started. And -1 plus 1 yielded 0, the equation resolving into perfect balance. It's not magic, she said, almost to herself. It's geometry. Hidden geometry that only becomes visible when you extend numbers into the complex plane. The builders would have appreciated that observation, Theron said. They too saw the equation not as a mysterious coincidence, but as a window into the deep structure of mathematics, a place where algebra and geometry and analysis all converge into a single beautiful statement. They stood in silence for a long moment, both contemplating the equation and what it represented. Spoke again. What else did the builders preserve about these relationships? What applications did they consider important enough to encode here? Theron's expression grew thoughtful. Many things. Exponential growth and decay appear throughout the natural world, from the reproduction of organisms to the decay of radioactive elements, to the charging of capacitors in electrical circuits. Powers and roots are essential to understanding scaling, how quantities change when systems grow larger or smaller. He began to walk slowly through the archive, Kira following. They preserved techniques for solving exponential equations, for finding the value of an unknown exponent that makes two sides equal. They recorded methods for approximating irrational powers, for calculating values like 2 raised to the square root of 3. The formations they passed display fragments of these techniques. Algorithms and relationships crystallized into permanent form. Kira caught glimpses of iteration schemes, Taylor expansions, continued fraction representations, all the mathematical machinery that humans had developed to grapple with the power of powers. They also, Theron continued, preserved warnings, cautions about the dangers of exponential processes left unchecked, examples from history where growth rates exceeded sustainable limits. They understood that the same mathematics that could describe a savings account growing through compound interest could also describe a pandemic spreading through an unprotected population. He stopped before a formation that seemed older than the others, its crystalline structure carrying patterns that looked almost like scars. This section records several collapse events, he said quietly. Civilizations that grew too fast, consumed too much, exceeded the carrying capacity of their environments. The mathematics of their decline followed the same exponential patterns as their rise, just inverted. Kira studied the scarred crystal, feeling the weight of history preserved in its structure. They wanted us to understand that the power works both ways, she said, that the same forces that enable rapid growth can enable equally rapid decline. Yes, and more than that, they wanted us to understand that exponential processes feel deceptively slow at first. A quantity that doubles every fixed period starts small, grows through seemingly manageable stages, and then suddenly explodes past any reasonable boundary. By the time the growth becomes obvious, it may already be too late to contain it. He traced one of the scar patterns with his finger. The builders called this the lake and lilies parable. Imagine a lake where the lilies double every day. If it takes 30 days to completely cover the lake, how many days until it's half covered? Kira worked through it quickly. 29 days. Because on day 30 the coverage doubles from half to full, so on day 29 it must be exactly half. Correct. And on day 28, only 1/4. Day 27, 1/8. For most of the process, the lake looks essentially empty. The crisis becomes visible only at the very end, when it's nearly too late to respond. The implication was clear. Exponential threats didn't announce themselves until they were already critical. Any civilization hoping to survive needed to understand these patterns deeply, to recognize early stages of explosive growth before they became unmanageable. Is that why this section of the archive is so extensive? Kira asked. Because the builders considered exponential understanding a matter of survival. Theron nodded slowly. They believed that many of their predecessors had failed precisely because they lacked this understanding. Cultures that thought in linear terms, that assumed the future would be a simple extension of the past, were caught unprepared when exponential forces reshaped their world. He turned back toward the main chamber, his voice taking on a concluding tone. What we discussed today, powers, roots, logarithms, the extension to complex exponents, this is all foundational. The applications extend far beyond what we can cover in one session. But the core understanding, the recognition of what exponential processes are, and how they behave, this is what the builders most wanted to preserve. Kira followed him, but her mind was still processing the connections. One more question, she said. The equation with E and I and pi. It's beautiful, but is it useful? Does it actually help with practical problems? Theron laughed, a surprisingly warm sound in the crystalline space. Immensely useful. That relationship is the foundation for understanding waves, oscillations, electrical circuits, quantum mechanics, signal processing, almost any field that deals with periodic phenomena. The ability to express rotation and oscillation in terms of exponentials simplifies calculations enormously. He sketched a quick example in the air. Consider a wave, like a sound wave or a light wave. Its behavior can be described using sines and cosines, which oscillate back and forth. But these trigonometric functions can be difficult to work with, especially when waves interact or combine. Using Euler's formula, we can express waves as complex exponentials instead, which behave much more simply under multiplication and addition. The trails illustrated his point. Two wave patterns combining. When expressed as trigonometric functions, the combination involves complicated identities and careful bookkeeping. When expressed as exponentials, it's simple multiplication. So the abstract beauty actually serves a practical purpose, Kira said. Almost always, in mathematics. Theron's voice carried conviction. The builders understood that practical and beautiful were not opposites, but partners. The most useful mathematical structures tend to be the most elegant, and the most elegant tend to find applications no one anticipated when they were first discovered. They had returned to the main chamber now, where the illumination had shifted to something gentler, suitable for reflection rather than active learning. The crystalline formations around them hummed quietly with stored knowledge, centuries of mathematical understanding preserved in their faceted depths. Thank you, Kira said simply, for showing me all this, for helping me understand why it matters. Theron inclined his head. Understanding is what the archive exists for. What we do with that understanding, that's up to each of us. The builders gave us knowledge. They couldn't give us wisdom. He turned to leave, then paused. Practice the calculations we discussed. Not with any device, but in your mind. Learn to feel how the numbers behave, how powers accelerate and roots compress. That intuition will serve you better than any amount of memorized formulas. He departed, leaving Kira alone in the chamber with the gently pulsing crystalline formations. She sat for a long time thinking about growth and decay, about numbers that couldn't be fractions, about the strange way that imaginary exponents produce rotation instead of expansion. The archive around her held so much more than she had explored. Other chambers contained other knowledge, other mathematical structures waiting to be understood. But for now she was content to sit with what she had learned, to let it settle into her understanding the way sediment settles through still water. The number E, that strange constant approximately equal to 2.71828, seemed to hover in her awareness. It wasn't a coincidence that it appeared in so many contexts. It was, she understood now, a fundamental feature of how change worked in the continuous universe. Growth at a rate proportional to current size naturally involved E. Decay at such a rate did too. Rotation and oscillation, when properly understood, were just more manifestations of the same underlying principle. They had been dedicating their lives to preserving this knowledge against whatever catastrophe they had foreseen. They hadn't just stored information. They had organized it, structured it, encoded it in ways that would make reconstruction possible, even if much was lost. The crystalline formations weren't arbitrary. They followed mathematical principles that would help future investigators understand their contents. The realization made her feel less alone. Across an abyss of time, minds had worked to ensure that understanding would survive. They had succeeded, at least in part. The archive still functioned, still transmitted knowledge to those willing to learn. Kira stood slowly, her body stiff from sitting. The chamber's illumination shifted in response, brightening to support movement rather than contemplation. She walked among the formations, running her fingers along their surfaces, feeling the subtle vibrations that indicated active data storage. In one section, she found patterns she now recognized as logarithm tables, vast arrays of pre-computed values that had once served as essential calculating tools. In another, she found representations of exponential growth curves, different bases producing different rates of expansion, but all following the same fundamental pattern. A third section caught her attention. The formations here were arranged differently, in spiral patterns that reminded her of the complex plane Theron had described. She recognized the relationship after a moment. These were representations of the complex exponential function, e raised to powers that included both real and imaginary components. The spirals twisted outward, or inward, depending on the real part of the exponent. Positive real parts produced spirals that expanded as they rotated. Negative real parts produced spirals that contracted. And purely imaginary exponents, like e raised to I times theta, produced perfect circles, neither expanding nor contracting, just rotating, endlessly. It was beautiful, Kira realized. Not just abstractly, but visually, aesthetically. The mathematics created patterns that pleased the eye, and satisfied some deeper sense of harmony. The builders had understood this too, encoding their knowledge in forms that were both functional and beautiful. She wondered how much more remained to discover. The archive was vast, and she had explored only a fraction of its contents. Other mathematical structures awaited, other relationships and patterns that would expand her understanding in ways she couldn't yet anticipate. But that was for another day. For now, she had learned enough to change how she thought about growth and change, about multiplication and its inverses, about the strange numbers that lived between and beyond the familiar ratios and fractions. She left the chamber as the illumination faded behind her, carrying new understanding like a precious cargo. The archive hummed quietly in her wake, satisfied that its purpose had been served, at least for one more day, at least for one more seeker of the knowledge it had been built to preserve. The corridors beyond were darker, lit only by the ambient glow of the crystalline structures that lined the walls. Kira walked slowly, letting her eyes adjust, thinking about all she had learned. Powers and roots, exponentials and logarithms. The mysterious equation linking e and I and pi, each concept connected to the others, forming a web of relationships that extended far beyond what she had explicitly explored. She paused at a junction, where 3 corridors diverged toward different sections of the archive. One led to the historical records, accounts of civilizations that had risen and fallen according to patterns she now understood more deeply. Another led to the physical sciences, descriptions of how matter and energy behaved according to mathematical laws. The third led to regions she hadn't yet explored, mysteries still waiting to be uncovered. Tomorrow, she decided. Tomorrow she would continue. But tonight, she would rest, and let the day's learning consolidate. The builders had understood that knowledge needed time to settle. That understanding grew not just through intake, but through reflection. She chose the corridor that led toward the living quarters, where she could find rest and food, and the company of others who studied here. The journey was long, but her steps were steady, and her mind was full of numbers dancing in patterns she was only beginning to comprehend. Behind her, the archive waited patiently, as it had waited for centuries, holding its treasures for those willing to seek them. The crystalline formations pulsed with quiet light, encoding and preserving, ready to share their knowledge with the next seeker who would come. And somewhere in those formations, preserved in patterns of light and crystal, the equation still shimmered. E raised to I times pi, plus 1, equals 0. 5 fundamental constants connected in perfect balance. A window into the deep structure of mathematics itself. The night would pass, the learning would continue, and the archive would endure, as it was built to endure, carrying its precious cargo of understanding forward into whatever future awaited. Kira smiled as she walked, tired but satisfied. Some days the work felt endless, the knowledge too vast ever to fully grasp. But today had been different. Today she had seen how pieces fit together, how disparate concepts unified into coherent wholes. That was worth any amount of effort. The corridor stretched ahead of her, lit by the soft glow of crystalline formations that had watched over this place for longer than anyone could remember. She walked forward into that light, carrying the day's understanding with her, ready for whatever tomorrow would bring. The archive had shared its secrets, at least a few of them, and she had listened, learned, and grown. That was the purpose, the reason the builders had worked so hard, sacrificed so much, to ensure this knowledge would survive. Their gift had been received, their trust had not been betrayed, and the ancient dance of teaching and learning continued, as it had continued through all the ages since humans first began to count, to measure, to understand the patterns that govern their world. Kira's footsteps echoed softly in the corridor, a rhythm of their own, another kind of counting, another kind of pattern. She let the rhythm carry her forward, thinking of nothing now except the next step, and the next, and the one after that. The mathematics could wait until tomorrow. Tonight was for rest, for letting the crystal lattices of memory solidify around all she had learned. Tomorrow she would return, and the archive would be waiting, ready to share more of its endless treasures. That was the promise the builders had made. That was the promise the archive still kept. And Kira, walking through the soft crystalline light, was grateful to be part of it. One more link in a chain of understanding that stretched back to the very beginning of human thought, and would stretch forward into futures no one could yet imagine. The walls hummed quietly around her, keeping their secrets, holding their knowledge, waiting for the questions that would unlock new revelations. Somewhere in those crystalline depths, more patterns waited to be discovered, more connections waited to be made, more understanding waited to be born. But that was the work of tomorrow, and the day after, and all the days that would follow. For now, Kira walked and rested, and prepared herself for the continuing journey. The archive endured, the knowledge persisted, and the learning, as always, would continue.